for many of us, that at a more local scale, at a more actionable scale, is one of the things, at least that gets in this space. So there's a lot of interest in actionable science, which I think is exciting. There's a kind of a growing convergence, a growing encouragement to do convergence research, and there's opportunities in this space for us to be involved. At the same time, I think that the CESM community is well positioned to address some of these needs, but we also need kind of training and more support and more opportunities to have conversations with each other about what's working, what are best practices, what are things that are working well, and lessons learned. And so I think for both Monica and I, getting this session together was very much in that vein of trying to share conversations about what we're all doing. At least for me, a lot of these come through in CGD exchanges, and so for those of us that are at UNCAR, we get to hear every couple of weeks about kind of exciting projects that people are doing, and I hope this is an opportunity to kind of expand that discussion to a broader group. So I wanted to highlight that there's a few posters. I think there's time this afternoon or this evening for posters. So Roy Rasmussen, Tim Schneider, and Monica Morrison all have started. Just remind everyone of the CGD Code of Conduct. And especially, I think the new ideas that we're talking about here are really exciting. So let's kind of celebrate those together. In the interest of time, and also wanting to kind of foster a discussion, I think this is an important session that we all need to be able to ask questions and communicate with each other. So I'm going to ask the speakers to keep their talks to 8 to 10 minutes. Once you hit the 10-minute mark, I am going to get a little grumpy and ask you to stop so that we can have time for questions in between. So with that, I'll turn it over to Monica.
Good. Okay, so we're going to start off quick so that we have enough time, as Will said, for any kind of questions or discussion after our presenters. And I have the pleasure of introducing Andy Newman as our first speaker, talking about developing a usable CTSM model and experimental configurations for the Klamath River Indigenous communities. So, Andy, you've got 10 minutes max.
No, I'll try to keep it shorter than that, because I really would appreciate feedback and discussion. So yeah, I'm lucky enough to represent this project. This is one of the early career innovator projects from cohort 2. So we are in our second year. So we have some experience about things that have worked for us and haven't worked. I have the full project team up here. The PI of all of this is Cleo Hazard. He is a professor at the University of Washington, Seattle. He calls himself model adjacent, which I think is always a good term. He has a lot of really cool stuff going on with communities, indigenous communities, social science, and other things, and has some appreciation for modeling, and his team has some appreciation for modeling, right? So it's a nice blend. It's maybe a little bit easier than some projects, but there's still a lot of talking past each other and trying to reset and really focus on common understanding, I think. So for full background, this is the full project title. It's quite a long project title, so I won't read it out. But essentially, Cleo's spent a lot of time in the West Coast kind of salmon, fish, river world, and a lot of time on the Klamath Basin specifically. So he and the team have a ton of built relationships, and I'm going to emphasize that a lot. That's a very key point, right, for these kinds of projects, is to have a long-standing relationship that you can leverage to bring in new people, and so we can make mistakes and not totally ruin the project. And so this project specifically is thinking about ecological restoration along the Klamath. So fire, landscape changes, like land cover, land use change, reconstruction of landscapes using historical knowledge. And the Karuk tribe is Cleo's main collaborator, and they have some really detailed knowledge of the basin, some really cool ideas on how to try to better understand traditional practices and maintaining the landscape, and hopefully then maintaining it to be more resilient to climate change. And we're kind of trying to focus on hydrology and fish. So for the next few minutes, I'm just going to basically hit the different pieces of our project. And I think the word iterative discussions doesn't ever change. So that's, again, like trying to emphasize this idea that it, for better or worse, we're at a point right now where it takes a lot of spin up on these kinds of projects. And maybe, there are ways through these kinds of discussions that we can build best practices and try and build infrastructure and build things that we can take some of that spin up time out of the equation in the future. So we're taking the CTSM model here, formerly CLM. I don't know if it's referred to as CTSM only. These are CTSM/CLM. So the community terrestrial systems model or the community land model. A community model, the core land model for CESM. And really trying to focus on vegetation, land cover, hydrology, and then fire was in the proposal, but it's come up again and again. And so we're trying to deal with fire at some level. It's really challenging for kind of the scales we're running at. And then, there's a lot of discussion centered on, how can we use this model to serve community needs. And so that is, everything falls out from that, which is why I have it bolded there. Then there's other topics that we spent the first year talking about: climate variability, observations from traditional community sources, trying to get just a lay of what is available, where everybody, views their role, what languages people use, how do people approach problems. It's fun and interesting, and also can be challenging, right? It's very challenging depending on what your mode of operation is. I'm kind of like a chop, let's do sometimes, and so that's a very challenging environment. And so again, iterative discussion, like, Cleo's group has a lot of community interaction and a lot of community engagement. They have, they go into the field regularly, like, at NCAR we're modeling support for this project, so we're not going to spend a lot of time in the field, so we really have to leverage that. There was one workshop last summer where we got to introduce the project and a little bit of the modeling capabilities. This is primarily a UW task, and that's totally fine, right? They're the ones that have the relationships, and we can just interface with that. So then thinking about, how do we bring that information and translate it via expert judgment or whatever you might want to do for the research scientists or the modelers here at NCAR. We spent a lot of effort here as well, right? So there's the Klamath River Basin on the right. We're trying to model this really complex landscape. And for reference, this would only be about 2 CESM grid scales wide.
Somebody's muted.
And so we ended up with this high resolution concept, so sub 5 kilometer, to try and actually model the seasonal cycle of snowpack, of water in the river, etc. But what does that break in a global model that wasn't necessarily built to run at those scales? What are the assumptions? How do we figure all of that out? It's through discussion, through even finding other modelers. We have not a lot of fire expertise on the original team, so we bug Donica a lot, and we have Danielle Tuoma involved now and other scientists, and they've found other community ideas, and all of these great things have kind of like evolved over time. And so, right, so we ask certain questions, talk about assumptions, et cetera, et cetera. And you really have to always think about, what was the original use of this model? And, what are we doing to it that might break things in it? And what are the assumptions that we're forgetting about that maybe make this, we think, oh yeah, that's probably good back in the envelope, but is actually like totally inappropriate use because you've run it at a different resolution or different time scale or something like that. And so just kind of a couple highlights. This is probably the most technical slide I have. This is a hydrograph for 1 year. So the CTSM simulations in red and observed stream flow. This is the Klamath River at Orleans, California, so far northern California, near kind of getting down towards the mouth of the river, is in black. And so you can kind of see a couple seasonal cycles. And out of the box, the model, this isn't that great. It's not awful. And so we want to spend a lot of effort making it better for hydrology so that you can take your subsequent output for fish or do whatever you want. You want to have faith in the model can reproduce history. I'm almost at 8 minutes, so I'll try to move through a little bit more. But then this question, so the hydrology we can actually handle okay. We have experience with hydrology and CTSM at this point. The fire model was, like I said, something that was kind of out of the expertise of the core project team at NCAR to start. And it kept coming up, and so we're like, okay, we really need to think about how do we address this. And the main crux is we're trying to model, they really want to know about fire spread and fire spread over time in the future, and that's really not what the CTSM fire model was designed for, right? It's a large scale, kind of probabilistic, essentially burned area across a grid scale. We're running it at 1 to 4 kilometers. That kind of model doesn't really work anymore. And so we're thinking about ways to essentially prescribe land cover change, to use the CSM2 large ensemble to try and estimate where, you know, likely burned areas are in the future, and then prescribe land cover change. And so that's kind of, it's taken a lot to get to that point. And, you know, there's a lot of iteration with the community partners, like, well, why can't you just use a fire spread model? You know, why can't you add all these things to, you know, CTSM or do things differently? So, well, first, I mean, it's a limited project, but that's a ton of work, right? To build a fire spread model into CSM would be, that's a whole development track for years. There are fire spread models out there, and so like they're starting to investigate using those and other avenues. Right, so this is kind of just this more experimental design where like you take your maps of where treatment areas might be or where non-burned area was, and we're going to try to combine all of this with some rules. This didn't really show out, but essentially like a lot of surveys with the community partners, you can say, okay, if we have this kind of treatment and it originally is oak savanna, then you can change it into these different plant functional types, which are essentially the vegetation classes in CTSM. Right, so you come up with these matrices, and so you can apply future land cover changes based off of what kind of treatment that a community might prescribe. And so just to summarize, this kind of concept that gets brought up a lot in RVCC and other projects, to go slow to go fast, you know, lay the foundation for good team understanding, and try to have these open, honest discussions on modeling capabilities. What are these critical assumptions that need to be known at the minimum and potentially mitigated? And I'm pretty model agnostic, so is your model even the most appropriate option, right? Should you actually use a different tool? This all needs to be kind of openly discussed and not try to push a specific development track. And so, you know, and then thinking about this fire idea here, right, there's a lot of exciting development applications that can be co-produced with projects interactions like this. So I think there's the model really, I think, could open up a lot of doors to like thinking about different science questions. Yeah, thanks.
Okay, thank you, Andy. So looks like we do have time for
Yeah, which comment were you? Yeah, so this was that thing where like this kind of embedded fire model, at least the one that I'm aware of, and I'm not a fire expert, it's essentially probabilistic at a grid cell scale. I don't think there's any assumption that fire spreads across grid cells, and I could be wrong on that, but that was my understanding. And so like you're thinking about these 100-kilometer on the side boxes traditionally in the global model, and then you go down to 1 kilometer. Now you need to actually think about coherent fire evolution.
So Andy, you've touched, I don't know if this is working or not, but you've touched upon this issue that I have seen a lot too, where when we're starting to do more actionable science, we're actually boots on the ground with stakeholders and people on the ground, they want us to be generalists. And we sit in a world in which we are expected to be specialists. And so this is like this big problem that I'm facing too, where almost every project I've been on has been like, oh, you said you were going to do this. Well, now I need sea level rise. And, you know, the money is for 1 month of your time. So it's just like, I just wanted to highlight that I appreciate you vocalizing that challenge that I don't think people realize. Mm-hmm. People have really complex problems, and sometimes being a specialist isn't what they need. And so where do we fit as a science community?
Yep.
Kind of just thoughts there.
Yeah, we need some generational change in how we think about evaluation and value. Yeah.
Okay, thank you very much. Okay, so as we switch over the slides, yes, I'm going to welcome our next speaker.
Alice.
Oh, no, I think they're, yeah, okay, I was going to say, I think they have the room plugged in. Thank you, because I did not notice that, and that could have been bad. Okay, so I just want to welcome our next speaker, Alice DeBouvier, who will be talking with us about hotspots in the ice using CESM for Antarctic marine protection. Okay?
Cool, thanks. No, it's fine. Okay. Hi, everybody. So, as you heard, my name's Alice. I'm here to talk to you about a project that I've been working on in the Antarctic. We're calling it Hotspots in the Ice, and it's looking at polynyas, which I'll explain what that is in a minute, around Antarctica and trying to understand how important they are for Antarctic marine ecosystems and if they need protection. So, this image here, right, that you're seeing is an image of Adelie penguins jumping into the ice around Antarctica. All right, so this project that I'm going to talk about, the overall goal is to provide information about the conservation value of polynyas in the different Antarctic regions on policy-relevant timescales. So what you're seeing here is a map of Antarctica, obviously, and these like magenta areas here are areas of high sea ice production. That's what polynyas are. I'll talk about them more again in a second. But what you are also seeing in blue and gray are marine protected areas around Antarctica. So the blue areas, this is the Ross Sea Marine Protected Area. It's been enacted. It was a huge process to get it enacted. And then these gray regions are areas where there's proposed marine protected areas. And then there are some areas like here where nothing has yet been proposed. I'm going to focus a lot here on the Ross Sea just to explain what a polynya is. So you can see there's this big magenta right here. So this is the Antarctic coast. I've flipped this now upside down. But what you're seeing here is a big polynya, which is an area that's bounded by land or sea ice that has lower sea ice concentration than the surrounding regions. So the black here is the ocean. You can see there are some other what might be deemed polynyas here. And why we care about them is that in the summer months, where these polynyas happen, you get these huge blooms of phytoplankton. So that's what you're seeing here. Both of these are from satellite images. But we're not interested in just the phytoplankton. We're interested in how the production in these regions propagates up the food chain. So for this project, we, in the model, Marble explicitly models different types of phytoplankton and zooplankton, krill-like zooplankton, and that's really a base of the Antarctic food web. We're working on fish with Feisty, but we're also partnering with biologists who are penguin and seal biologists to understand how these larger predator species are using these regions too. All right, so the other basis of this project. So this is a NASA-funded project. It's part of their Applied Sciences program. And what they want you to do is work with end users to create some sort of tool that the end users will use. So our end users are the Pew Charitable Trust, the Antarctic and Southern Ocean Coalition, and then Only One. So these are NGO organizations, and what they do is they provide information to CAMLAR, which stands for the Commission for the Conservation of Antarctic Marine Living Resources, and they're the ones who actually enact marine protected areas. So this is a group of, I think, 27 nations now, and what they have to do to get a marine protected area is have unanimous consent that an area should be protected, which, as you might imagine, is really hard to get a bunch of countries to agree on something like this. They also, the Pew Charitable Trust, ASOC, Antarctic Southern Ocean Coalition, and Only One, also lobby the general public because this is really a public policy science interface where the public can kind of put pressure on delegates who go to CAMLAR to encourage them to protect different areas. So that's a really big part of how that Ross Sea Marine Protected Area was actually enacted, is that there was public pressure. All right, so these particular end users, what they want is they want us to be able to help them socialize science with educational storytelling about polynyas, and they want this to work for 3 general audiences. So they want the general public. The general public, kind of the goal is to have this storytelling, but they want them to take action, sign petitions, encourage their delegates to support protection around Antarctica. And they want this tool to also be interesting to policymakers. So again, you want that storytelling aspect of it, but then have links to white papers or submit white papers to CAMLAR that support scientifically why these areas should be protected. And then for scientists, again, socializing this, but have links to the data or code repositories. But that's not necessarily the top level. They want this to be really Visually appealing, again, you see these figures here, the pictures that John Weller, who's a part of this team, he works for Only One, has taken in Antarctica. And those sorts of strong images really help people feel passionate about wanting this area to move. So a huge part of this is they want this web-based tool that really focuses on storytelling for these regions, obviously with science, but it needs to be visually appealing. You don't want just what we all are pretty comfortable going to and like clicking a box and getting a spreadsheet. They don't want that. But they do want these interfaces so you can like click on different regions and get deeper and deeper into the story. So if you are a scientist, you can eventually get the data if you want, but the general public, you don't want a landing page where they're like overwhelmed with boring science figures that doesn't inspire them to take action. So I will say I put this together. This is not what it will look like. But the final tool we're working on is this map, where we're going to focus on several regions. So the Weddell Sea, Prids Bay, D'Urville Station, the Ross Sea, the Amundsen Sea, and then the Antarctic Peninsula. So most of these areas either have MPAs or have proposed MPAs, except the Amundsen Sea, which does not yet. And so we're trying to kind of look all around the continent, but have different regions we're going to tell stories about. And a lot of this will be putting together media that helps tell the story. But you can click on different areas, and so you could add layers where what you're seeing here now are polynyas. So the red lines show where we find polynyas from satellite observations, and the orange are where we're identifying polynyas from CESM. And this is the 1 degree model, and I want to point out that they overlap pretty darn well. So it seems like even in our low resolution model, we're finding that there's open ocean in areas where satellites show it as well. So this is still a valuable tool for us. And then we're able to use the outputs from Marble in the ecosystem model, and hopefully Feisty, to look at how this is going to change over time. So what you're seeing here is net primary productivity, and I want to point out that we are seeing it's enhanced in these regions right here. Some areas more than others. You don't see it so much in these regions, which is just interesting. And then they want you to be able to click on a region. So here, if we're looking at Prids Bay, you click on that, it'll zoom in. This is where web developers at Only One who have experience with story maps will help make this more visually appealing. But once you click on a region, you will be able to dive deeper. So here we have biology variables. So I'm still showing NPP, but you could click on the model projection of krill, and you can look at how that will change in the future with the CESM2 large ensemble. We're getting emperor penguin demographic projections using the CESM2 model outputs. We don't have seal demographic projections, but we do have information about how seals use polynyas in this region particularly. And so there'll be different layers that you can get into to understand why this region is special and needs protection, using output directly from our models, not exclusively, but trying to put it together in a storytelling way. We'll also have some just basic environmental variables, like how's the temperature changing, how's the ocean acidifying, stuff like that. So there's an example of how you might click on penguins, and it shows penguins don't have a good future ahead of them. And then here's examples. These are the biologists we're working with, but this is an elephant seal. You can see the little radio tracker on his head. So they have tracks of how the seals are using the polynyas, like what sort of behavior they exhibit in there. Are they diving for food, stuff like that. So using this combination of different information sources to understand how things might change in the future and what we want for protection. So that's kind of the goal of this project. As I said, it's NASA funded. We have to work with these NGOs. One of the things that the organizers asked us to talk about was what kind of makes these projects different and unique, and how to make this work. So I just have some bullet points about how to make this work. So the first thing is communication is key. So I think one thing is to set up your expectations early on. Some of the end users were like, oh, should we set up a Slack channel? And they were like, hell no, we hate Slack, do not do that. We just want emails. So you just need to figure out, if you're working with, I think, different end user groups, how they want to be communicated with. I think this has come up with RVCC. There are some people who really don't have access to regular internet. That's not for this project. But setting those expectations and figuring that out early is really important. We have regular science team meetings. One of our team meets monthly with the end users, and then we have a larger group of the scientists meet with the end users about twice a year, and I think that's good for keeping everyone on the same page. All right, next one, trust and relationships. So I think one thing is kind of I hadn't mentioned this before, but one of the people on this project, Cassandra Brooks, she works in policy. She's at the CU Boulder. And I think the reason that this was something that was appealing to the end users is she's worked with them for around 10 years. So it took a long time for her to build trust with them. And so then when we had this idea and we approached them, they were willing to work with us. And they were like, we haven't used climate models before, but this sounds really interesting. Yeah, we're willing to work with you. There's a cost share part they have to contribute to this program. And so they were willing to put up the money to engage with us. And I think if they didn't know her and they didn't have that established relationship and I had just approached them, they'd be like, no thanks. So I think it's really critical to emphasize that the relationship is key here. And now that I've worked with them, I might be able to do that. But I think, just someone from this room randomly approaching them is probably not going to necessarily be successful. And then it takes a lot of time to build those. Yeah, I see. Be realistic. So I mentioned that it's this international group that has to approve MPAs, and there's like a war going on in Ukraine, and Ukraine and Russia are both on CAMLARs. So we have to basically accept that during this project, no MPAs are going to be adopted, but we can still do good science that when politics change, it might be possible. Keep in mind your audiences, again, general public versus policymakers. I want to point out too, goals can differ. So, scientists want to publish papers, but that's not necessarily the focus of this goal. It's more about using existing tools and making them useful rather than necessarily publishing exclusively. And then you have to be thoughtful about how this course scale can be useful for something like this that's actionable. And this is a big team that's working on this. It's not just me, so I just want to be able to acknowledge all the people that have worked on this. Thanks. I don't know that there's time.
I'll just say thank you for empathizing some of the serious pragmatics of doing these types of projects, especially with respect to the pragmatics of communication, because you can do all the work to translate, make things accessible, but if the information doesn't get to them because you're using different forums, it can be a huge problem. All right, so I'd like to introduce our next speaker, Elizabeth Woolner from University of Colorado, who will be talking to us about the Front Range Ecosystem Resilience Project that Will alluded to earlier. So there you go.
Hi, sorry, I'm a little short. So hopefully everybody can see me all right. Full disclosure, I am a qualitative social scientist. So a little different probably from most people in this room. So, if I don't get into details on models, that's why. But we do make our own models, and you'll see one of mine at the end. So today I'm going to be talking about the Front Range Ecosystem Resilience Project, working with physical science, social science, to make better science and to have some codified definitions of refugia and other kinds of ecosystem resilience. So what is the Front Range Ecosystem Resilience Project? Like I said, we have got 3 pillars. We've got physical science, social science, and stakeholder engagement. We have both physical scientists and social scientists in doing the stakeholder engagement. This is an exciting thing. It's not just us social scientists doing this, it's everybody is involved. You can see some of the activities up here that we're involved with. My little plug for this project is that this is a really fascinating project to work on right now. We have this confluence of opportunity in the Colorado Front Range, where the Colorado Front Range is a really diverse landscape as far as who owns the land. We're really looking at public lands here, and public lands and the role of local land management agencies are very different in other parts of the country. Here we have a very strong local land management focus and an increasing focus on these issues at the same time. And then you pair that with our physical scientists who are looking at refugia and resilience at kind of a local scale. This is a really exciting thing, and I just wanted to make a plug on that. So as far as what we've been doing for stakeholder engagement, some pictures. This was from a few weeks ago on May 24th. You can maybe recognize some of the people in the room here, but this was our stakeholder engagement workshop. We invited a lot of different stakeholders, but we got 12 of them, 12 managers and people who work closely with managers in the room to make sure that what we are doing in the Front Range Ecosystem Resilience Project is actually relevant and applicable to what they're doing. So these are all people who are local Colorado Front Range public lands managers. We had some awesome conversations. We did a lot of great brainstorming activities. Here's an example of one of the questions that we asked and some of the sticky notes that we did. This was like Christmas for me. This is all data. This is the data that I work with, are things that people just write on sticky notes. But just to give you an idea, like what some of these people were saying, we asked them, what do you think a refugee is? If we're trying to codifine this, it's pretty important to get your definition of it too. So we talked about that. We talked about, what are your challenges? I put these challenges up here because I think that they're pretty relevant to a lot of other things. We'll get into some of the information challenges in a second. But resources came up time and time again. I know we were just talking about the pragmatic issues involved in stakeholder engagement, but like we are restricted by our capacity, funding, and time, so are managers. And they also have a lot of prioritization that they have to do among different projects. They have to make decisions on a very short timeline often. They have to deal with scale, what's happening in their own park, and then they're trying to think about what's happening outside of their park or management area as well, but they might not have good information sharing. And then there's a disconnect or potentially even a lack of leadership among policymakers, the public, and management. There's just not great information sharing, and people have different priorities and are not always communicating them. So it's important that we as scientists are communicating our priorities so we are not contributing to this mess. As far as information challenges, just accessing data in the first place is really challenging. Like I said, there seems to be, this is from the workshop in particular, some of them talked about a lack of leadership within agencies, and then there's not a ton of communication among agencies, which is disappointing. We have this big connected landscape in the Front Range, but agencies are just not doing information sharing or don't have any way to facilitate that. They are also dealing with shifting baselines. I think we're all aware of this. The ecology of these areas are changing really quickly and people don't really know where to start. As far as just really general, broad level, what data would be useful, a lot of people said the finest scale possible. They're managing a park or a management area and potentially looking at individual species within that. So as fine of a scale as possible is really useful for them. However, having local data embedded in these global, state, larger contexts is also important because they do care about what's happening outside of their park. They do care where they fit in, even though it might not be relevant for them on specific management timelines. And then maps. Like I mentioned before, they have a lot of different prioritization issues, and so literally visually layering exactly where their priorities might lie helps them make decisions under rapid timeframes. So this is the model. I make conceptual models. I don't really make, the models that you guys make. But I just wanted to kind of point this out, kind of see where we all are at this model. So again, this is mostly with public lands managers. Private lands, totally different story. But this is a combination of some of the findings I'm having from these interviews that I've been analyzing and other research that's been done at the University of Colorado Boulder. Essentially, we have these three things going in, external factors going into a management decision: public values, political and institutional context, and research. They all provide information, and they all provide guidance and constrain what a manager can do. However, managers are taking what is most useful and accessible of all of these three pillars, not just from research. As much as we would like that and as much as they would like that, the public values in the political and institutional context is very, very important, what they do. So they're harvesting from all of these sources, combining them, making a decision, combining them with their own internal values, worldviews, orientations, and a decision is made. From there, everybody kind of steps back and evaluates, right? The public will step back and say, does this actually work with my value? Maybe I didn't want this trail here before, but it actually turned out to be okay. That decision and their idea of how the process actually worked, if they felt, respected, if they felt like their voices were transformative, all of that goes back into their public values directing conversations again. And then researchers also evaluate the decision. I think we're familiar with kind of the research side of this, of they did a prescribed burn. Let's see if it actually worked. But we also evaluate it in terms of the process, either in an academic sense or in the sense of how did I feel like my research was being heard in this particular case. One thing to note with this is both evaluations are value-based. And this is something that's really important for us as scientists to understand, is that we also have values at play in this situation. And sometimes they're good, sometimes they're useful, and then sometimes perhaps they are holding projects back at the same time. So the suggestion here is to add kind of a third step. We don't want to stop this cycle because the cycle isn't inherently bad, but we want to take the step after we evaluate some kind of management activity on public lands to use this as an opportunity to improve our usefulness, to build relationships, and to decrease the bias that we might be putting into the data that isn't useful, or just even to recognize our bias in the first place. Not all bias is bad. Like one of the other projects said, building relationships is really key in this area. And so I just want to highlight that. And again, thank you. I'm excited to kind of step into this process with all of you.
For a question or two, yeah, Tim, please.
Hi, hello, Tim. So I'm looking at your model here and I'm wondering, I guess, two things. One, how do they're two very different questions, sorry. One, how do these values get sorted out in the decision maker's mind? And two, you know, there must be a role where data enters this. And like, since it's a CESM workshop, right, say climate data. So when you get to the top center where it says decision, where does the data flow in and how do they know, I mean, where do the values come from?
Yeah, those are great questions. I had another version of this with annotations that I figured I didn't have time to put up. But there is, so this is some of the decisions-based literature where essentially managers are negotiating between, yes, these like 3 external factors, but then their own internal factors. So it's almost like the top arrow leading out of the managers, that's where their own personal values would come in. And then the researcher and the public values would come in as soon as they're evaluating those decisions. Those are kind of embedded throughout the whole process. But the manager's values are particularly, as they're synthesizing everything and kind of making a decision from there. Data, on the other hand, I would probably put that mostly in this research management connection here. Because that's where, if they're going to use a tool, that's when they're going to use it. You know, some kind of mapping tool, some kind of climate data visualization tool, that's when they're going to use that. And that provides really helpful information for a lot of them if they know how to use it. And so our job then is to make that link as not tenuous as we can to strengthen that. Did that answer your question? Cool, thank you.
Okay, do we have any additional questions? So I have a quick question for you, if you don't mind. I'm curious if you found any really useful and like adequate ways to combine different perspectives or value systems, because they can be greatly inconsistent with one another, which is kind of a difficult landscape to navigate. So, or any just maybe just having awareness of it is useful.
Yeah, definitely first step is awareness on that, especially in the scientific community. There's a lot of different values even among disciplines in the scientific community, and I think that's why working on these like multidisciplinary and interdisciplinary teams are so important, because we get that practice right away in our own space. So when then we move out of that space, we start to realize, oh, maybe this isn't 100% what we thought. Actually, this workshop we did, I think, was really interesting. I remember, Will, you were saying, like, what climate data do you use? And they kind of looked at it and were like, what are you talking about? Like, it was just a really interesting moment. I mean, and they understood data and they understand information. Like, these people are professionals, they know what they're talking about. But it's just a very different worldview. A lot of them are, you know, working on the ground, they're seeing things, and for them that's data, for them that's information. And as a social scientist, for me, that's also information. Like I said, like, this is my data. And so just being aware of those things to start, I think, is a really, great start. Yeah.
Great, thank you. Okay, so next up we have Dave Bailey, but we're gonna quickly fix the screen so that we don't have the Zoom bars over things. So, here it is. Why is it not? Perfect. Okay, thank you. So, Dave Bailey on navigating the new Arctic, convergent pressures on Arctic development. Okay, thanks, Dave.
So I'm going to talk to you about a broad brush overview of our overall Navigating the New Arctic project with, much thanks to the National Science Foundation for funding this work, working on. So this is a multi-institution, I think I counted 12 institutions that are involved in this project, and probably like 20 principal investigators. So it's a big project, and we're spread across a lot of different institutions. But the way we designed this was to divide it into 5 work packages, as we're calling them. So the first is sort of based mostly at RAND Corporation, the loci of Arctic development. Then there's the climate scenarios part of this, which I'm primarily the lead on, but also with Tamlin Pavelski at University of North Carolina. And then there's the transportation and accessibility aspect of this that we're sort of closely linked with the transportation and accessibility part of this. And then the 4th work package is the case studies, which I'll go into a little bit later. And then finally, the work package 5 is just sort of the integration of bringing everything together into one big story. And that's mostly coming into play in sort of year 5. There is an important part that's not officially a work package, but this international reference group, and that's led by Lawson Brigham at UAF. And so it's important to emphasize what this is about. So what we have is representatives on this reference group from all around the Arctic nations. And they're our main points of contact to go out into the indigenous communities, into the stakeholder communities, and so forth. And so this is who we're using as that body to be able to contact these people. So it's been a great thing, and it's worked out quite well, and I'll talk about it basically on the next slide a little bit. So one of the first things that they did, this is the RAND Corporation, they're really good at surveys, this is their thing. So what they did was they sent out a survey to many Arctic communities, and again, it was sort of focused through the reference group was the main way to do this. And we got a lot of really interesting responses back on these surveys. Some communities were very offended by it. Other communities were much more excited. And so I think one of the themes that came out of this is there's sort of many Arctics, and that is that each of these indigenous communities around the Arctic has a very different perspective on the idea of development in their community. The idea that ships might be coming in there, or trains, or whatever. So that's an important takeaway point from the survey that they did, and so they wanted to be very careful and respectful when doing this. So that's one of the main jobs of the reference group in particular. And then the part that I'm leading is more about the climate scenarios. The idea is that we know the sea ice is changing, we know the Earth is warming, but the idea is, can we say anything more substantial about the regional impacts of this? And how is it going to impact the shipping lanes? As the sea ice melts back, that opens up more sea ice area. But also on land, the fact is that it's going to actually reduce the amount of ice roads available, and there's going to be more sloppier terrain if you want to try to build a railroad through this or whatever. So what we're trying to do is use many climate simulations, ensembles, and so forth to try to get precipitation, temperature, snow depth, sea ice concentration and thickness, to then use these to help guide some of the other offline models that are more sort of in the next work package that I'll talk about. And then as a part of this, I've had this summer intern, Emma Perkins, who's been wonderful, who's done a lot of work in doing some analysis of this and creating some Python notebooks to extract data sets so that we can then send these on to the other work packages. So the transportation accessibility work package is, partly about the shipping aspect, as you can imagine. The Northern Sea Route is already open, basically. There's a lot of shipping traffic already going through. And so the shipping companies want to know how many days they're going to be able to get their ships through, and what the sort of cost involved in doing this. But it's a much shorter route to go over the pole than it is to go down through the Mediterranean and through the Suez Canal. So it's a very desirable thing. And so one of the aspects that they're looking at is trying to assess sort of how long is it going to stay reliably open, how many days of the year, and how is that going to change as we go forward into the future as well. And another aspect of this work package is the land part of it, which I'll actually talk more in the next slide about. And so the case studies, we've identified certain communities around the Arctic. One in particular, this one, it starts with a K, but I think it's pronounced Sherknes. But this is the Sami community of northern Norway. These are one of the communities that are actually quite excited about the idea of development coming through there. And there is plans to build a railway from the south all the way up there so that they can then have ships stopping in and having an opportunity to develop their economy. So they're quite excited about this, whereas communities in Alaska, they're just so, but anyway, the idea is that there's, ice roads to be thinking about, railways to be thinking about, and so these are all parts of this. And then we have representatives in Norway that are going out into these communities and talking as well. So with that, I'll just sort of summarize that, each of the work packages has progress. We've been delayed a little bit with sort of COVID over the last couple of years. We're in year 3 of the project, but we are going to have a group meeting in August where we're all going to get together and share some of this, and then we're finally going to hopefully get into that final sort of integration stage. So I'll stop there.
Okay, thank you. Microphone. Okay, looks like Elizabeth does.
So I'm actually affiliated with the community office through NNA. And I was wondering, how much maybe they've been interacting with these projects. Like how much have you used the resources that they have? Are they accessible? That kind of thing.
Well, I did attend the NNA community meeting in November of last year. And so, but in terms of using the resources, not directly, I would say. But hopefully it's something, again, as the integration occurs over the final year, that's something
Oh, and Eric, yeah.
Realities are opposite, right? About that, you just store all the stuff until the ice road comes back.
Yeah, I mean, that's a good question. I think that's one of the things that they're trying to problem solve in the third work package, but basically, yeah, my piece of it is to supply them the climate data and then let them try to figure it out from there. but yeah, that is an interesting contrast, and it's going to be a difficult question as we move forward.
Okay, so next up we have Kristen Krumhart, who's going to be talking about potential use-inspired applications of CESM linked to fisheries. Okay, so it should just be okay like that, like you had it. I know. Good. Just he'll
So
make
just
it
do view
big
or-
screen for us.
Yes. All right. Everybody, yeah, so today I'm going to be this list of collaborators here that's helped me get to this point in the research. And this is still like, I'm just talking about potential applications because everything is still kind of in the beginning stages here that I'll talk about today. So first, I just wanted to kind of give an overview of what we're doing that's novel here. And so basically, this is CSM, the Marine Ecosystem the model in CSM that does the planktonic marine ecosystem. So this is just run online within the ocean model. And we're linking this offline to the feisty fish model. And yeah, so it's done in an offline sense. So we use output from CSM to force the feisty fish model. And recently I've been to develop this application a bit more, developed this recent, new ecosystem model for the plankton, which resolves two zooplankton types. So splitting the zooplankton, we have like in the standard version, there's only one generic zooplankton, but we split it into the small ones, the microzooplankton, and the larger ones, the mesozooplankton. And this allows it so we can because the bigger ones can be food for fish. So that is an input into the feisty fish model. And then also I wanted to bring attention to the particulate organic carbon flux to the bottom because sometimes the fish they feed on the bottom. Organic matter is actually reaching the bottom of the ocean is important as well. And then just jumping over to the feisty fish model side of the slide here. In feisty, there are three forage fish, the large pelagic fish, and the demersals. And then these are size classes. And so, so the first type is this forage. An example of that is like a sardine to illustrate this group, and they only get to size medium, smaller fish. And then the second kind of fish that's in the pelagic part of the model are these large pelagics, and so those have three size classes, so they can get really big. And an example of that is the tuna here. And then the third type of fish is the demersal fish. So that means that they spend or at least a good part of their life on the ocean floor feeding. And so an example of this type is a cod. And so that's what I've shown here. And so they start off in their larval stage in the pelagic, and then they migrate down and when they're medium-sized off the benthic invertebrates at the bottom of the ocean. Which are themselves feeding on the POC flux. And then once they're an adult, they can go between both and pelagic realms. And so feisty is really neat because it has growth, so fish can grow from one size class to the next, and those are represented by the orange arrows on this illustration. And then it can also, once they get to the largest size class, they can reproduce or allocate some of the energy towards reproduction to reproduce of the larval fish stage, and that's shown by the red dash. So I'll just touch on two studies where we're going to be using this model. So the first one is the Ocean Climate Data Dashboard. And this is a project with these collaborators I've listed on the bottom, specifically Kelly Benning at the University of Auburn, who's a social scientist, and helped facilitate some of the The idea here is that planning in national marine sanctuaries requires and these sanctuaries are managed by diverse stakeholders, so we need a way to take into account all these different stakeholder values. And then so our project here is to co-design this climate data dashboard with the national marine sanctuary managers and other stakeholders. And this includes both workshops to introduce the dashboard and get feedback on it, as well as some survey data. And we're doing this first for two national marine sanctuaries in the southeast U.S., the Florida Keys National Marine Sanctuary and the Flower Garden Banks. And I will talk about Flower Garden Banks. So Flower Garden Banks National Marine Sanctuary, it's in the Gulf of Mexico. You can see it's situated up here off the coast of Texas and Louisiana. These are like deeper coral reefs, so depth coral reefs that like deeper than the Florida Keys. And they are growing on these salt domes or banks in the Gulf of Mexico. And these are like super diverse environments. You can see some of the pictures here that I included. So lots of habitat for species, fish and other marine invertebrates, all sorts of corals, sea turtles, dolphins are in the area as well. And the National Marine Sanctuary was established in 1992. Just a few of these banks, and then more and more reefs have gotten added since then. So the reef is managed by the National Marine Sanctuary in this region, and that they're advised by the Sanctuary Advisory Council. And I'll show a little bit more on that for the next slides. And so they use this adaptive governance framework, which just basically means that they take in the latest science and adapt their policies accordingly. So here's a couple pictures of some of the Sanctuary Advisory Council meetings. And so these, like I said, there's a very diverse stakeholder group in this region. Like a lot of people care about what's happening in this area. So the council is formed of fishermen, recreational divers, scientific researchers, the sanctuary managers themselves. There's oil and gas representatives, educators, and then also the public can come to the meetings and stand around the edges of the table. And so at first, the interactions that we've had from some of our colleagues on this project have indicated that they're most interested in like climate-driven changes in fish populations, as well as like things like ocean acidification, water temperature, because they've just started to see some coral bleaching events in the region, and also storm activity. So we're planning to use CESM for these to show projections of these. And just to give you kind of, I did run Feisty on one member of the large ensemble last week, and I got some changes from the 1950s to the 2090s, and that's what I'm showing on these maps here. Basically, long story short, like all three types of fish in Feisty show declines from climate-driven changes, but that's actually kind of a conservative estimate, I think, because when we look at the temperature, this is a time series of temperature from the Flower Garden Banks region, and it does, obviously it increases with climate change, and this can cause more and more coral bleaching, and the reefs are actually a sanctuary or a nursery for young fish. So that's not included in the Feisty fish model, but it could be definitely an important part of the story. If these reefs start to break down, then there would be. The second one I wanted to touch on is the second potential application is from the Rising Voices Changing Coast project that we talked about this morning, and specifically the Alaska Regional Hub. So again, this project is the convergence between like Earth system science and indigenous knowledge. And so for the Alaska region, we've been focusing on this Shishmaref region that's in this box right here. And so in this region, the native communities are super reliant on both marine and terrestrial ecosystems for their subsistence. And just to give an example, like they hardly have any grocery stores there, and what they do have, it's very, very pricey. So they really are dependent on their native food supply for their subsistence, and climate change is definitely affecting that. So the community has expressed concern about many climate change related things, including coastal erosion, which is the background for this slide, showing the coastline just washing away in this kind of barrier reef island area. They're really concerned about sea ice loss because they butcher their seals on the sea ice, and if it's gone, they can't do that. They're also very concerned about harmful algal blooms and ocean acidification, and then they've also expressed concern about changes in fish abundance. And so the idea that we're having at this region for like a deliverable of this project is to make this convergence research atlas that will include like climate projections from CESM, but as well as interviewing elders about what changes they've observed. And so just to give a quick example of how the fish model might be useful, this is an old cookbook that is from the Shishmaref Day School showing different fish recipes that they use in the And then on the right-hand side of the slide, I've run Feisty on a forced ocean sea ice CESM simulation over the 1958 to 2021 period, and these maps are just showing mean biomass of each fish type, but you can see that it's largely dominated by the demersal fish, so the ones that kind of dwell at the bottom, typical of a shelf system like this. And so that would be like a flounder, which I found in this cookbook. And then there's the mean pelagic fish biomass, which is quite low, actually. That would be kind of maybe something like this whitefish here. And then the forage fish are of also decent biomass in the area, and that would be like a herring. So I feel like this could potentially be a useful avenue of looking at the output from the Feisty fish model. So just to wrap up, I've kind of shown you how we're linking the CSM marine ecosystem model with Feisty, the fish model. And for every region, they're not only interested in changes in fish, but they're also interested in other things happening at the same time, like sea ice loss and ocean acidification. On these plots right here. So that I talked about the National Marine Sanctuary Project and the RVCC Alaska regional project, but there's also other potential uses, such as doing fish predictability runs in coastal areas, such as large marine ecosystems. This could be useful for the other RVCC regional hubs, such as Hawaii, who also observed fish declines in recent years. And then also, yeah, the Antarctic Marine Project that Alice spoke about already will be Feisty for that as well.
If anybody has anything to ask, well, if nobody has anything to ask, I'll ask a quick question. So I'm curious, in the first project that you identified with the flower garden, you said that there's a lot of diversity across the different community partners, stakeholders, in terms of their values. Have you found it difficult to tailor CSM and Feisty output to meet all of those like values or information demands?
Yeah, I mean, so far we're just getting started, so we haven't actually interacted much with the stakeholders. The first workshop will be this summer, but yeah, I can imagine that there's going to be some values, especially between the oil and gas, for instance, and for example, and maybe the researchers or the education people, because yeah, I mean, we definitely have a very diverse group here, and it's going to be hard to come up with the same sort of values for sure. So, yeah.
Thank you. Mm-hmm. All right, so I'd like to invite up our next speaker, Lee Kessenich, who will be talking about a multi-index examination of future fire season length and severity over the United States. Figure out how the two screens relate to one another. There it goes. Oh, perfect. There we go. Yeah. Sorry, this is not an intuitive setup. Way does it go? Is that going to bother you? Okay, thank you.
So, Science for Wildland Fire Operations and Policy. Apologies for the extremely dry science title of my abstract. I'm going to be focusing on a different aspect than I originally was planning on. So I'd like to acknowledge all of the co-authors. This is a multiple institution project. Melissa Bukowski, Seth McGinnis, and Linda Mearns here at NCAR. Allison Cullen at the University of Washington, and John Abatsoglu at the University of California, Merced. So, adapting regional climate simulations to usable information for practitioners and stakeholders on the ground is a really complicated idea. We are funded by the NSF Growing Convergence Research Initiative, focused on a project for the projecting the future risk of simultaneous large wildfires, and our team of scientists includes climate modeling here at NCAR, public policy and fire ecology at the University of Washington, and fire science at California Merced. So what we as a convergent research team need to address is a paradigm shift in fire management where our stakeholders are contending with the reality that the past is no longer a reliable reference for future fire. And so climate projections could be useful for informing this shift, especially as we try to push for proactive management instead of reactive management of fire. And those stakeholders include policymakers, fire management, and in the field practitioners working within various agencies. A subset of their logos are seen up here, and this includes scales from local all the way to national in the United States. That all seems like a neat, organized package still, but it's not. It's complicated, it's messy, and extremely challenging. I'm so excited that I actually get to say that in this session. And we've invested a lot of time into developing a common language across all of our disciplines. We have fine scale, meaning 100 meters or 25 kilometers, depending on who you're talking to. Short term could be tomorrow or 30 years from now, and long term could be 6 weeks from now or 2100. So it takes time to find areas of focus for us and how our various fields of expertise complement each other. And we've spent a lot of time and effort to ensure that our data is understood across fields so we can all converge. Not just our climate projections, but there are a lot of messy, incomplete fire management data. There's lots of gray literature, fire ignition and burn area data. The list goes on. And so in all these discussions we've had, some of the climate-related questions we've wound up asking are how and where can we make climate change more of a focus in fire management? What sort of decisions in fire management move on timescales appropriate for climate change information? And how do we communicate our climate data so it can be used appropriately in applications? We don't have great answers, we probably won't, but what I'll be showing in the rest of this talk is focusing on this last question, focusing how to visualize climate projections with our stakeholder audience in mind. By working with our stakeholders iteratively and convergently, we're building trust and confidence with them, and we're aiming to reduce the possibility of misinterpretation of our data and increase its usability. So that data is the North American branch of the Coordinated Regional Downscaling Experiment, or NA-CORDEX. This ensemble samples uncertainty across different GCMs and RCMs. All 13 simulations use the RCP 8.5 high emission scenario and are dynamically downscaled. For those who are interested, these are all CMIP 5 era GCMs, and they're listed in this table. The outputs of all these simulations are shown in the gray boxes in the flow chart on the screen. And the fire indexes are representations of various aspects of fire weather, such as moisture deficiency, fuel moisture, flame length, and fire intensity, all projected on a daily timescale. And these fire weather indexes are familiar to our stakeholders. They know how to interpret it in their work. For this first visualization, I want to walk through the iterations on these ensemble maps, which take in stakeholder feedback at every step of the process. These are aimed at national and regional management and policy audiences. And keep in mind that for every visualization type I'm going to be talking about today, there's at least 5 that didn't make it. One of the first visualizations we showed to our stakeholders was this count of days above the historical 97th percentile for the fire index energy release component, projected for the mid-century period 2040 to 2070. This was to test the waters to see if it was useful. The information presented is relevant, and people like looking at maps. They know how to read them. But a single climate simulation isn't appropriate for practical application, so we need to present all of them together. Handling all the models together was fun for us scientists to look at, but it was difficult or confusing for our stakeholders to interpret. We were warned that if we put this out there on a wide scale, some people would avoid interpreting the ensemble, pick a model that suited their biases, and go on. So we had to consolidate and do that interpretation for them, which is how we get to our ensemble maps, which consolidate the 13 models into a single figure. And we have a two-dimensional color bar now. The color on the x-axis of the color bar shows the magnitude of change. The color saturation on the y-axis of the color bar indicates the level of simulation ensemble agreement. Oops. Areas of gray denote ensemble disagreement on the sign of change, and it's designed to draw attention to areas of most change where simulation ensemble agreement is highest. So it's doing a lot of that interpretation for them. We've also changed the reference periods to 2080 to 2010 and the future period to be 2030 to 2060 in order to make it more actionable for our stakeholders. Paneled all of our fire indexes side by side. We've added a hatching indicating statistically significant change, which would indicate change outside of expected interannual variability and is more likely due to climate change. The indexes in the left and middle columns behave similarly. They all feed into one another as part of the United States National Fire Danger Rating System. And a lot of these that have a lot of gray space are very sensitive to precipitation, which is projected to increase in this ensemble. The right column is a bit more dramatic, and the simulation ensemble agreement is much higher. The Keach Byram Drought Index at the top oversimplifies drought too much and is sensitive to temperature increases, so the projections make it blow up. The modified Fosberg in the middle and the Canadian Fire Weather Index in the bottom show a lot of areas of statistical significance, but it's not all in the same places. So these divergent responses across the fire indexes mean that we kind of have to encourage the use of multiple indexes, or for our more local stakeholders to use the indexes that are most well suited for their particular region or application. And for stakeholder feedback on this, it's very dense. Contained relevant information, and they could understand it with a little bit of thought. So we could also simplify this to suit their needs, and that is the case with many of our visualizations. We made these maps to address a number of our stakeholder interests. This addresses the length of fire season and the frequency of extremes. And the percentile thresholds that we used, or the midpoint threshold it's not percentile based, but it is still localized. It is mapped to relevant information such as fire season or levels of fire danger with adjective descriptors. And the count of days above a percentile threshold is easily understandable by our stakeholders and is relevant for planning. The local percentile threshold approach makes for a relatively uniform spatial interpretation, which is good for regional and national purposes, where they're looking at areas where there's a lot of variability in terms of what kinds of fuels and ecology is involved. These maps don't address the timing or peak of extremes and seasons, so it might be less useful for stakeholders who work on a more local scale. And to do that, we need to look beyond an annual count to see when things are happening during the year. That brings us to pocket cards, which are a tool used currently in the field and are very familiar to our stakeholders. So this is an example pocket card. It is used to contextualize current conditions with the observed climatology of a region. This can actually be put in the pocket of a firefighter in the field, which is why it's called a pocket card. It typically displays the maximum and average curves for a fire index, along with the 90th percentile for the season presented, which can kind of be considered a threshold for fire danger. And so this was a potential format for us to adapt. After multiple iterations, we get to the ensemble pocket card. Like in the example, this shows the maximum and average curves, fire season 90th percentile. The observations have been replaced with our model ensemble, and that they show daily statistics. There's a slight increase in future average ERC values, an increased season of fire risk, and potential for unprecedented fire conditions. So wrapping up, what I've presented today is hopefully just a start for more integrated information, and we're currently looking at existing tools in the field where we could add value. We're also looking into analyzing and projecting the wildland-urban interface out to the end of century. So this is year 3 of a 5-year project, and hopefully we have a great foundation to work with going forward.
I have oh, yeah. Do you want to come to the microphone?
Thank you for realizing all the difficulty and mentioning that. My question great conversation and great time and effort that you are putting. How some of these are feeding back to the improvement of the climate model? Or are you assuming that anything produced from the climate model, those are good enough for the stakeholder?
Yeah, so the NA Cortex archive, I don't think is currently being worked on in terms of more dynamical downscaling or more runs. We're currently just trying to make what already exists work for our stakeholders and also recognize that there are areas where we simply cannot be the data that they need.
Okay, thank you. So I'd like to introduce our next speaker, who is Keith Musselman from University of Colorado, who will be talking to us about rising temperatures. Oh, okay, I have an old title. Sorry. But the theme, I suppose, is rising temperatures, Alaskan rivers, and indigenous communities with a slightly different title.
Thanks. Thank you all. So this is a really exciting session, so I appreciate it. Another project sponsored by the National Science Foundation's Navigating the New Arctic program. And we're working interdisciplinarily, like many of the talks that we've seen today, on combining monitoring, modeling, and indigenous knowledge, so multiple ways of knowing. To start this, I'm just going to kind of give more of a framework rather than get into the results of the project. But to start, we looked for ways to engage with indigenous communities. And what we found were existing networks, and we found the most traction that we had was when we connected with working frameworks. So we found that the U.S. Geological Survey was working closely with the Yukon River Intertribal Watershed Council. And so through connections between scientists and researchers who are indigenous-led or indigenous-led councils, for example, we were able to connect and network with, in this case, 74 tribes and First Nations focused on the Yukon River watershed. And they have a board of directors that meets annually and details the most important research for the region. And so we worked with them to co-develop research questions. And so they were guided by that executive board of directors. We initiated that discussion, and you wouldn't be surprised that there was a long list of research questions. They told us that if we focused on fish habitat, rivers, and rivers was one of the things that united a lot of the different topics. So we brought together expertise to understand how rivers are changing. They told us that they shared with us that rivers are changing, they're impacting their communities, particularly communities that are off the road network. So they rely on rivers to transport supplies, particularly during the winter season. And then in the summer season, they're transporting supplies by barge. So ice roads were really important during the winter. And navigation was important during the summer, as well as subsistence fisheries, so salmon fishing on these large rivers. And that tied into other concerns about water supply, water quality, permafrost thaw. And so this is a large problem identification, which required a large team. So we gathered people from different disciplines, so social scientists, hydrologists, climate scientists, fishery ecologists, and indigenous contributors. Particularly, one of the things we did was to build an indigenous advisory council. So we put out notifications to communities that we were looking to hire consultants through the University of Colorado. So these were paid positions, and we met about 6 times a year, so every other month, and are doing that for the life of the project. We met first with these different representations. This is just showing cultural groups, this map of cultural groups and languages across the region, and the triangles are indicating our council members and where they are coming to represent those regions. And so this is made up of, our council is made up of indigenous youth, elders, scholars, and they come together with a lot of expertise to guide some of the research questions and ensure that the research that we're doing is serving the indigenous communities that we are intended to help.
The project itself is looking at how rivers are changing, and we're doing that through this concept of narratives or storylines, and that got a lot of traction because a lot of the indigenous knowledge is shared via narratives, and so we could find ways to do that. And so we've got here a kind of a Venn diagram of different monitoring, observations. Observations is also key because we leveraged indigenous observing networks in the region. Climate river modeling was critical to understand how rivers are changing. Again, rivers are really an integrator of the landscape processes, and using models like CESM or CTSM to understand how the landscape is changing in response to forced climate change. And together in the middle here are communities, and then our Arctic River Summit, where we brought communities together to get insight onto how to address this complex topic over such a large region with diverse interests, diverse politics, and again, crossing international borders as well. So there's some challenges to understand how we can bring climate science to bear to become actionable. Our monitoring, we are deploying river temperature and salinity measurements, so specific conductance sensors, to communities who have been monitoring their rivers for over a decade now. But they've been doing it as grab samples, and then that gets processed at a lab. So we're sending these sensors out to indigenous communities, all the dots on the purple dots on the map here. And we're developing community-specific reports that are then shared back to those communities. And at the same time, we're benefiting from those data to help inform and provide baseline for some of the models that we're doing. We're doing that both with those communities, which you can see here helps to kind of fill in a large data gap that is laid bare here with the USGS gauges. USGS does not monitor a lot of the Yukon River, particularly because of challenges in the hydrology itself. And the unstable banks. So we're sending these sensors out to all these communities and to USGS gauges, and they've been monitoring now for 3 summers. Those observations, again, are critical for providing a baseline, informing the deployment of the climate model that is run by a group here at RAL, led by Andy Newman and Yifan Chang. So they're using the regional Arctic system model, which is RASM, which has WRF at its core. And then within that, we've pulled out the old VIC hydrological model and put in the new CTSM, so the land surface model. And then using that with a streamflow model, Mizoroute developed here at NCAR as well. And then applying that output to sequentially run the river basin model, which gives us a river temperature and river ice model. And then finally, that output is then passed to our fish ecologists who are running a fish bioenergetics models to understand how salmon are changing. One of the reasons for that is that at the same time that we put this proposal forward, the salmon, particularly the king salmon or the Chinook salmon and the chum salmon, stopped returning to the Yukon River basin. And so the fisheries, the subsistence fishery, was shut down for the entire community, all the communities along the Yukon River basin, and has been for the last 3.5 years. So what we thought would be a projection of the future has now become a reality just in the last 3 years. So now this is a very relevant topic, and it's something that is getting a lot of attention from communities when we go out and meet with them. One of the exciting components, and this is kind of a pinnacle of this 5-year project, was to get together and to meet with community members. And so we held in December the Arctic River Summit, which was held in Alaska at the Alaska Native Heritage Center. And we had 100 people show up. This is people from resource management agencies, from communities, community leaders, spiritual leaders, elders, youth, and about half of the attendees were Native, and we were able to talk about and exchange knowledge of the current, of the historical, and the potential future conditions for the rivers, the fish, and the people who rely upon them. And ultimately, we set up the meeting so that we could inform the modeling of the climate model. So, for example, we use some of the information to send out surveys to communities to get insight onto what kind of resolution was necessary. And ultimately, we chose a 4-kilometer gridded output of the, or setup of the RASM model. We're also interested in resolving things like river ice and fish bioenergetics, and so that requires kind of honing in on particular fish species of interest. So we used a lot of the interaction and the exchange at the summit to understand what fish species were of interest, what river corridors and when were being used, and so then we can hone in, even telescoping in beyond our 4-kilometer grid scale to the scale of individual communities and river reaches and specific fish of concern. And we're using the information to develop action plans that were centered around the state of salmon, the state of rivers, and partnering indigenous knowledge with Western science to ultimately to inform management of these resources. And then finally, youth and elders thinking about building a bridge of traditional knowledge. And that was one of the things that was shared with us, is that with the shutdown of the subsistence fishery, the cultural impact of that is not really well understood by Western science and by the public. And so what that means is that the fish camps that have always been held every summer are no longer being able to be held. So the elders used to share their knowledge and teach the youth how to fish, and that was an engagement. They would go to these fish camps every summer for an entire month, and the entire community went downriver or upriver to their place that they've been fishing for hundreds to thousands of years, and that's not able to be held anymore as a result of the fishery collapse. And so there's a lot of interest and concern about what to do about that. I just wanted to acknowledge many of the scientists who are working on the project, as well as, again, our Indigenous Advisory Council members. Thanks for your attention.
Okay, so as we're switching things up, question? Yeah, Andy, please.
Have any thoughts on how we can change or start to begin to change the Western institutions to try and do things differently, be more efficient, incorporate all of the things that we're talking about here today?
Yeah, I would reiterate what was said earlier. I think some of the biggest challenges are the building of trust and the continuation beyond the project timelines of 3 to 5 year funding cycles, and thinking about how do we build on the momentum and the progress that we're making and the trust within communities to continue this. And I think a lot of the big hubs that we're seeing emerging, such as Rising Voices, is really important. And I also call out the USGS Climate Adaptation Science Centers as well as another place where we can see these regional hubs being built, and then that can continue the science.
We have a tiny bit of wiggle room. Can you wait till the end to ask it? Okay, sweet. So I'd like to introduce our next speaker, Yager Richter, who's going to be talking about the ARISE simulations for stratospheric aerosol injection, climate intervention simulations for actionable science, and stakeholder engagement.
Thank you. Hi. So this is work that's done with a group of people. Many of them are outside of NCAR at the aligning organization. So I'm going to talk about ARISE SAI, which are the climate intervention simulations for actionable science and stakeholder engagement. And just a quick motivation. So I think as many of you in the room know, the global mean surface temperature will most likely reach 1.5 degrees over pre-industrial somewhere between 2025 to 2035, and 2 degrees over PI in 2060. So solar geoengineering could be part of the strategy to offset some of the worst consequences, and ideally this would be done in conjunction with other methods such as carbon dioxide removal or cutting emissions, but it could be part of the temporary solution to keep the climate at a somewhat stable value. So this research was done as part of the Safe Climate Research Initiative, and the main outcome of this was this data set called ARISE, assessing responses and impacts of the solar climate intervention on the Earth system. And Silver Lining brought together this large group of people consisting of universities, NCAR people, people in developing countries. And the common thing between the people is everybody had a shared goal to see if we can evaluate the impacts, potential impacts of climate intervention. The experiments were co-designed with the community. Simulations were both performed on Cheyenne and also on the AWS cloud platform, and we're also putting data on the cloud in order to enable as much participation and evaluation of this data set as possible. And the analysis has been with the community from the very beginning, so everybody on this slide here and others had early access to the data. As soon as we had it available at NCAR, we shared it with the community. And more details will be available on the Tuesday 5:30 to 7:30 p.m. session, including the reception hosted by Silver Lining. All right, so one of the aims for these simulations was to do a more realistic experimental setup that would be co-created with the community. That would be something that the stakeholders could be looking at for potential impact. So we were trying to do better on the original data set that we did back with Simone in 2016. It was called GLENS, the Geoengineering Large Ensemble. But that one had a few unrealistic features. One of them was the climate intervention started in year 2020. We're also going against an RCP 8.5 scenario through the end of the century. So a lot of the papers out there focus on this this last period where there is really a high signal to noise ratio, and those studies were done for a different reason to really show what these critical impacts might be, but they're not necessarily the most realistic representation, because ideally we would definitely not want to be geoengineering throughout the rest of the century without other mitigation measures. So we try to do better in this set. And we try to look at what background scenario we should look at, when do we start intervention, how much to cool, what should be the injection strategy. The small problem with getting input from the community was that this was right in the middle of COVID lockdown, so we were doing this work in the summer and fall of 2020. So Doug and I spent many hours on the phone. Both of us spent many hours on the phone with Silver Lining. Silver Lining spent hours talking with the community. And there was so many hours that in the end, Doug wrote an entire paper on scenarios for modeling soil radiation modification after talking to more and more community members who do scenario development. And at the same time, we had limited time because the other teams were waiting for data, so we're in the meantime looking at GLENS. And we had also limited computing, so there were the limitation, but time was probably the largest one. And during COVID, we couldn't hold a bigger community workshop at the time. All right, so these are some of the variables that we were struggling with. So what temperature target do you cool to? Do you cool to 1.5 C, 1 degrees, half a degree C? What's the background scenario do you use? How many of scenarios are needed? When do you start the intervention? Do you terminate early? Do you account for interruptions? Do you account for phase out? So you can see that this starts getting into a very large space, and you can come up with many scenarios. And really multiple scenarios make most sense, but yet we only had limited computing. So what we did choose is a few simulations to run out of this diagram, which the original ARISE SAI were carried out on Cheyenne. We decided to cool to 1.5 degrees. We went with a moderate scenario of SSP 245, and we made a choice to stop the simulations at 2070, so do not go into that space where you're really geoengineering so much that it's unreasonable, but looking at the time period and at the amounts that might be part of that solution, part of the equations where CDR and other measures are building up and reductions of emissions. We also reduced the injection of aerosol injection to 21 kilometers. In GLENS, there was a little bit higher, and it is unachievable by current technology. So we did a lot of consultations with the people who are actually thinking, how would you get aerosols into the stratosphere to cool the planet? And that is about the lid where they think that would be reasonable. And we're using the full chemistry version of CESM to Wacom, which make very expensive simulations. So from the beginning, we at NCAR did very basic analysis to show that indeed you can do a lot better with intervention than without. So these are the changes relative to 2020 to 2039. So we can reduce the temperatures globally to much lower than they would be if we didn't intervene. And then we let the community do the remaining analysis. So for example, Rutgers is looking at land changes and crops. Cornell and NOAA are looking at stratospheric responses. CSU, they're looking at fire risk, permafrost, extreme weather, other matrices, and we're also working with the UK Met Office to do comparisons with UKSM to see where the answers might be similar or different. So the engagement was from very beginning. However, the focus was mostly on science and processes, and these are the people currently involved. So going into the future, we're starting to, at NCAR, at least look at more information that could be usable by stakeholders. So this is some of the work that Mari Tai has been working on with collaborators at RAL to, for example, look at water availability. So what this figure shows you is something that water managers might be looking at. So firstly, what this figure is showing is scale of CSM based on 20 rainfall and runoff indices to see how CSM is doing in present day. So we do not so well in the middle of the United States. We do really well in the Pacific Northwest and particularly in California. So Mari ran a stakeholders workshop for a different project, for a water availability project, and one of the things that the stakeholders are wondering, how much can you trust the model? So we're making the leap of faith here that if the model is representing something well during the present day, then we can trust it into the future. We really don't know that's true, but we think that's maybe a reasonable assumption, might or might not be. So for example, we can look at these regions, this region, Pacific Northwest and California, and we can look at that in these simulations, the SSP 245, and then ones with the stratospheric aerosols injections. So the ones highlighted in blue are the two regions, Pacific Northwest and California. And we can see what these boxes are showing is the proportion of total rainfall that comes from events that are heavier than the 95th percentile. And you do see that stratospheric intervention can reduce the intensity of these events, and especially in the Pacific Northwest. So again, you see the reduction in all the other regions, but we don't know how much we can trust it because the model is already not getting the information in the present day climate. So then looking forward again, this is on our wish list. It would be to utilize expertise across NCAR to create the information directly usable by stakeholders. So we're hoping to utilize downscaling methods and to provide the local scale information. This is what really people are looking for. Also utilizing different tools to make the simulations accessible. So this is a screenshot of the climate inspector that is ran out of RAL by Olga Wilhelmi's group. So we're talking with her to just inputting these simulations. In the past, she just has some output from RCP 8.5 simulations with CCSM4, etc. We just need resources. So the tools are already there. It's just a matter of resources to do all of these things, to give access to the data and to other people across the world. And then lastly, this is something that Jean-Francois Lamarck actually was pioneering, is to putting the silver lining together to make the data accessible to anyone from anywhere and to democratize data analysis and access. So this is the one thing that people who are most affected by climate change and probably by climate engineering, they're in places where they're not getting a voice, they're not here in this room. So we have put the original data set on AWS. So the pros are that the data can be accessible and can be downloaded by anyone, even without an account. And analysis is on the cloud is possible, but it's not so simple. So on the cloud, analysis is not in everybody's skill set. You gotta know how to run Jupyter, you gotta know Python. And right now we don't have the resources to provide the available notebook support, so there is room for possible integration with the Earth System Data Science Initiative. But the people in developing countries, they're perhaps not, that is not in the top skill set, is how to be using these new complex tools. And also, if you're going to do anything that's computationally intensive, that requires credits. And AWS right now is not giving more credits. So end user support from our end is currently unavailable. So there's two more data sets that Brian Dobbins is working really hard on uploading, and hopefully they're going to be available soon for people as well. So this is it. This is the last slide. So there are many dimensions of climate intervention space, and really multiple scenarios are needed. And the one key message out of this project I've learned is the community input and support. It truly takes a lot of time, and you need to have the dedicated resources to maintain those relationships and keep talking with the stakeholders and the community. And data on the cloud is a big step forward, but unfortunately doesn't solve everything. For example, Daniel Visioni is still carrying hard drives around the world to deliver the data to people where they need it, right? Because people have not come around. So I think I'll leave it here because I see Will standing up, but I just say thank you to these two folks, Brian Dobbins, who's been spending hours and hours to get the data on the WSM process, and Daniel Visioni, who has become sort of our community liaison and is doing the brunt of that work of communicating and answering questions about the data set, and that is probably going to become a bigger and bigger job in the future. So thank you.
Question? Yeah, Andy, if you want a microphone, because we have to swap over to our next presenter on Zoom, but go for it.
Questions for a lot of people that aren't here. And I've been thinking a lot about this lately, ethics and wisdom of doing things like this. You mentioned it a little bit, but where is the space for that? Right, I mean, yeah.
Yeah, exactly. So that is the thing. It takes a lot of time, even from the beginning. I think that was the biggest unexpected, how much time and effort is to bring that community, to put the data out, to get the stakeholders, get all the pieces of the information. So I think that's something we're going to struggle for a long time.
Okay, so I am going to introduce our final speaker for this afternoon. So online we have Shana Sadai, who is going to be talking about using climate modeling to inform climate litigation and advance climate justice. So Shana, we see your presentation, but if you want to put it into full screen mode. Perfect.
I'm just going to move the Zoom bar out of my way. Thank you so much, Monica and Will, for hosting this session. I am going to be speaking about using climate models. I recently finished my PhD at UMass Amherst and started a postdoctoral fellowship at the Union of Concerned Scientists, working on litigation relevant science. And so I'm going to be talking, I'll mention a few particular CESM projects, but mostly I'm going to be talking about the broad of litigation relevant science and how it is just like one avenue of putting actionable science into action. So here we go. Go forward. So climate litigation has been happening at an increasing rate in the past decade or so. And currently, most of the cases that are being brought to courts around the world related to climate change are happening in the United States. But there are an increasing number of cases that are coming from the global south in recent years, as well as international efforts, which I'll go over in a couple of slides. And so this is a realm where people are trying to push for action through the courts alongside policy measures, sometimes to advance how policy measures are happening, and sometimes to address mitigation or adaptation or loss and damage. And so there's a few different types of cases, categories that are happening currently. A lot of climate litigation revolves around human rights. So often it's plaintiffs coming to court saying that insufficient mitigation or adaptation action is violating their rights to life, health, food, water, cultural heritage, safety, things of that nature. So a lot of them are revolving around human rights law. There's also a number of cases revolving around domestic policy enforcement and infrastructure projects, particularly around keeping fossil fuels in the ground, and a number of cases around corporate liability, responsibility, and greenwashing, like some of the cases that attorneys general have brought against ExxonMobil in recent years. And so cases can take a while to move their way through the court system, and that can happen at the local, state, national, or international levels. But some cases have already had pretty major wins. And I wanted to point to this one as an example, which was a case where 8 islanders from the Torres Strait region took the government of Australia to court in front of the United Nations Human Rights Council, saying that Australia's failure to adequately mitigate or assist with their adaptation was violating their human rights. And this case, they ended up winning, and the court sided with them and said that yes, insufficient mitigation and adaptation on the behalf of Australia is violating their human rights. And so this verdict just came down in September, so we're still waiting to see how that decision ends up being implemented. But this was a major international win, and this case relied on both Western scientific knowledge and Indigenous knowledge and especially their firsthand testimonies of what they had seen and experienced in the Torres Strait Islands. And I would be remiss if I did not mention that this case is going on trial today. This is Held versus the state of Montana. It is a case where 16 different youth plaintiffs, from toddlers to teenagers, are challenging the state government of Montana because Montana has legislation on the books which bans the evaluation of greenhouse gas emissions and corresponding impacts to the climate in their environmental impact assessments. And so the youth who are bringing this case are saying that that is a violation of their constitutional rights to a safe and stable climate. And this is the first case in the United States of the Youth v. Gov cases that has gone to trial, and it is the first U.S. case claiming that there are constitutional rights to a safe and stable climate. So I'm wishing them all the best of luck as their trial begins today, and it will be going on for the next 2 weeks. I also want to point to efforts within the international space, and in particular, the efforts around international judicial bodies and requesting advisory opinions. And so there are several of these. I'm just going to go into 2 of them for a minute here. And so this one was brought last December by the Commission of Small Island States on Climate Change and International Law, and they are requesting that the International Tribunal for the Law of the Sea issue an advisory opinion on these specific questions. What are the obligations that state parties to the United Nations Convention of the Law of the Sea have to prevent, reduce, and control pollution of the marine environment with respect to climate change? And what obligations do they have to protect and preserve the marine environment in relation to climate impacts, particularly pointing to ocean warming, sea level rise, and ocean acidification? So as countries are currently trying to get their legal briefs submitted to the International Tribunal for the Law of the Sea so that the tribunal can issue their advisory opinion, these states are going to be drawing from the scientific literature related to how climate change is impacting all of the marine environments in different kinds of ways. Another one is the International Court of Justice advisory opinion request. This was an initiative that was started by law students at the University of the South Pacific, and then the government of Vanuatu offered to champion this on the international stage, this initiative that the law students wanted to put forward. And Vanuatu, along with 18 other core group negotiators, started drafting what questions they wanted the International Court of Justice to issue their advisory opinion on. And that advisory opinion would help to dictate sort of how climate change is seen within the context of international law for decades to come. And so Vanuatu and the core group made a huge effort to reach out to all states around the world to participate in drafting these questions. And these are the questions that they've asked the ICJ to issue an advisory opinion on. What obligations do states have under international law to ensure the protection of the climate system for present and future generations? And then what legal consequences are there for states that cause significant harm to the climate or environment? And in particular, they point out the geographic circumstances of small island states that are adversely affected disproportionately by climate change, as well as the intergenerational equity aspect. And the World Youth for Climate Justice have been hugely supportive of this and have done a massive campaign to try to get youth to also participate in the efforts around this advisory opinion. So states are also getting their submissions ready for the ICJ, and then the ICJ will look at all of those submissions being put in from states and youth around the world and come up with their advisory opinion. And so all of these cases relating to climate litigation, no matter what level they're at, from local to international, they're all relying on different kinds of climate research to prove what the plaintiffs are bringing to court. And so I want to mention here CESM, because I'm a little way through, so I want to bring that in. So my own work from my PhD dissertation was using CESM for freshwater forcing experiments, particularly to look at the impacts of Antarctic meltwater on future global climate. And when I was doing this research, I was never thinking about it as being relevant to assisting with climate litigation, but it turns out that it really was. And so within my first chapter, I was running these simulations, but I was really interested in what are the climate justice implications of them. So I teamed up with political scientist Regine Spector and worked with Dr. DeCanto and Gomez to really dig in terms of justice theory. What are those implications? And I wrote a paper about it, particularly focusing on distributive, procedural, and recognition types of climate injustice. and showing that while Antarctic freshwater forcing has the ability to slow down global temperature rise, when the Paris Agreement is defined in terms of global mean temperature rise, what does that delayed warming signal mean when you're still having massive sea level rise from Antarctica, which freshwater forcing is then driving that delayed warming signal? And so that's explored in this paper. And then my later work, which is about to go into peer review, is fine-tuning the timing and magnitude of the feedbacks and tipping points that were identified in the earlier work and used in the climate justice paper by doing two-way coupling between CESM and the PSU 3D Antarctic ice sheet model. And through this work, I was able to much better characterize the timing and magnitude of these feedbacks. And so the relevance of this to international legal efforts has been in terms of helping lawyers to understand the feedbacks and tipping points that are inherent in the climate system and the implications that that has for intergenerational equity and human rights, and as well as the mitigation obligations that states could potentially have, particularly in the paper when I'm talking about climate justice and pointing to the normalization of overshoot pathways and how the climate damages incurred during overshoot periods can exacerbate risk and can lock in future sea level rise, which is then a human rights issue for future generations as well as for present generations. And so this is just one of the figures that'll be in the paper showing that that negative feedback on global mean surface temperature is weaker than in the one-way coupled simulations, but we're still getting pretty substantial sea level rise. And so in terms of the broader landscape of what types of research are needed to assist with climate litigation, there is some work that has been done to interview lawyers who are experts in climate and environmental law and identify the main scientific research gaps that those lawyers are running into. And these fall into a couple categories which are almost all related to climate attribution. So the source attribution of what particular emissions are from particular governments or corporations, then what are the climate impacts of those emissions, and also looking at extreme event attribution, because extreme events are where a lot of damage is occurring and people are seeking remedies for those. And so some upcoming work that I am considering doing with CESM, that I hope to do with CESM, is to look at, in particular, the emissions from the fossil fuel companies. So there exists an emissions data set put out by the Climate Accountability Institute, put together by Richard Heady, which quantifies the emissions over time of the largest 88 fossil fuel and cement producers. And earlier work by the Union of Concerned Scientists looked at running just a very simple parameterized climate carbon cycle model to get at what those emissions meant in terms of atmospheric CO2 concentrations, global mean temperatures, and global mean sea level rise over the historical period. But we want to take this from just being able to get the global mean of those three particular numbers to be, and there's other work that has been done as well since then, but to look at this from a geographic point of view, by moving from having these emissions within a simple climate carbon cycle model to incorporating them within a fully coupled Earth system model, CESM. So that's work that I'm thinking about doing over the next year. So hopefully more on this to come. But there's many ways that Earth system modelers can participate in assisting with climate litigation by lending your expertise to help lawyers write amicus briefs, to help lawyers understand the research, serving as expert witnesses. It's very possible that your own current work may be relevant to supporting current and upcoming cases, and your future work could help fill research gaps. So there's lots of resources there, and feel free to reach out if you have any questions. Thank you so much.
Thank you very much, Shayna. We do have time for a quick question. If anybody, yeah, Julio, go for it. Please come up to the microphone.
Thanks for the talk. I was wondering what sort of approaches extreme event attribution might take. I mean, is there consideration of using like numerical simulations of actual events that try to untangle forcing from, decades of emissions, et cetera? I'm wondering what approach you would take to attribute.
Yeah, so I don't personally do extreme event attribution, so I'm less how much more likely a particular event would have been because of anthropogenic emissions is very helpful.
Okay, thank you. So I think Will and I wanted to close, see if there's any comments that anyone from the audience would like to make. Yeah, Rachel, please come up to the microphone. And then I see Kevin coming up behind you. So we'll let you two close out the session with your comments.
So I think this was a really great session. And I guess one of the things that Lee touched upon this a little bit, but I feel like because this is the CESM meeting, we're talking about CESM. But how does this community think about climate change uncertainty? Doing this work with one model is problematic. Telling stakeholders you can give them, I mean, I guess it's how you phrase that information, and maybe your model is the only model that can do that, but in the fields in which I work on, I would say do not disability. So that's just something to think about when you're getting more involved in this stakeholder climate, is like, what do we do with uncertainty?
Yeah, I think that's a really good point. And in talking about a lot of the information for actionable purposes, there's also calls to couple climate model information with other sources of information so that you kind of have that variety of evidence going on. So not only having model pluralism, but also information pluralism, if you will, both important features of kind of the actionable science realm. Thank you. Yeah, Kevin.
I have maybe two quick remarks. I think the first is what came clear through a lot of the talks was actually how much effort and time goes into doing actionable research, right? And that I think that's, you know, impressive, the amount of effort that people in this room have put in. But I do think it kind of raises a couple challenges, right, about how you, can scale this up, and a couple of the speakers talked to that. But B, it also addresses the way in which the physical scientists in the rooms are evaluated at their home institutions. And I think there's kind of the metrics aspect. And I think that this is an area where I think CESM as a community could maybe lead in thinking about that. The other aspect that came up that I thought, well, I think came through a couple of the talks was actually related to the use of climate scenarios and what climate scenarios were developed to do, what we're actually using them to do actual science. And I think it actually kind of raises the question of, is it a time for us to maybe start thinking about future scenarios in a different way in which have focused a lot on detection and attribution and trying to understand what are the implications of not mitigating. But a lot of the actionable science we heard about today is focused around adaptation and resilience. And those require totally different types of scenarios. But within the CMIP framework. And I think that's, again, an area where maybe the CESM community could really start to think about how to try to create a little bit more nimbleness in scenarios.
Yeah, thank you. These are both excellent points. I think to the first one, the current paradigm that we exist in, at least in the climate modeling world, is maybe not well adapted to a lot of actionable science stuff. Whether you're thinking about how scientists are being evaluated, whether you're thinking about how time can be allotted to these things that take a lot of effort, like communication, translation, relationship development with the end users. So there does seem to need to be kind of a cultural or a paradigm shift within the sciences to allow for this to be scaled up in the way that you're suggesting. And to the second point, I think that in the actionable science context, there needs to be a lot of discussion, and this is kind of my own personal area of research, but of the adequacy for purpose of a lot of the things that we are using to do actionable science, whether that be the scenarios, whether that be the models or the data, or even the way in which we're translating the model output for end users. So these are a lot of kind of, as you suggested, the upstream things that a community like CESM can start to work on and take a hold of and really make room for within our scientific practices and culture. So I thank you for those comments. I think that we are at time, and so I will leave with what I think was a take-home message that Lee provided with us, that convergence is hard. But I think we can see from a lot of the talks that were given that convergence, whether we're thinking about model integration, we're thinking about communication with end users, and the bilateral development of a knowledge base between local communities and global modeling efforts, it's valuable. So it's certainly worth our time despite the challenges and the time that need to be allotted to shifting towards this new paradigm in Earth system science. So thank you all for joining us, and thank you to our speakers. Okay.
Oh yeah, of course. I'm gonna be leaving for the evening, but Fletcher will be here to help.
Thank you.
Good session.
Thank you.
Of course. All right, and I'll close this out and pull out the, where did the mouse go? There it is. There. And those the three slides for later. The other ones, there's 3 in person, 3 online.
Okay, got it. I noticed that the 3 online are right when we come back from this break. So let's just go ahead and try to do all the
Can I suggest one thing really quick? I'm not sure if it's something that you can do anything about, but like these displays, like they're not, the way that they're lined up is really weird. So I don't know if with respect to the displays, you can align them so that when the mouse is here, you can drag that down and the mouse will appear here. Because we couldn't figure out how they were oriented and like where the mouse is going. So just, do you know what I mean? Like when you go like this, it goes up to that screen.
Yeah.
But
Because right now this is on the right and this is on the left. I understand that can be confusing.
that's what we had trouble with. That's it. I'm sorry. It's just like, it's
No, that's something
it's
that we
not
should have done on our end.
No, it's not the way they're actually like physically lined up. And so Will and I were like, oh my God, we're idiots. Like, but just so that the next people don't embarrass themselves like we did.
There you go. That.
So yeah.
That
Oh
works
yes.
like that now.
That is like.
All right.
Yes.
Well, I gotta get out of here, but Fletcher will be here for the afternoon.
That's awesome. And that's not me. I think you have. You have career estimation, which is.
Yep.
I haven't even seen any of that.
Excuse me.
Stop by later.
Sounds good. Does that say time on there?
Yeah.
Does it say 4 o'clock for them?
No, it's 3:30, I think. Oh, it does start at 4.
Okay,
How
cool,
weird.
cool.
I think the other one started at 3:30. Or no, wait, it's 3:30 now, isn't it?
Yeah, just passed.
Yeah,
Yeah.
so 4 is when we reconvene.
Sounds good. Thank you. Are you helping as far as like letting people into the bot maybe? Or are you? Oh, no. More moderate process. Okay, got it. We have 3 visitors first, back to back to back. I'm going to try to Okay, so it'll be a little different when we switch back from.
join from one of the links that was emailed out?
Yes, it should in. Memorize that by the end of the day, and then.
So want to join with
Yeah,
computer audio?
you've got to do that, and then say got it, and then go down to the bottom left. Oh, you already did.
Okay, and so okay, perfect.
And then, go to. That way you can see the participant list, and then chats will come in down there.
Okay.
And then that way you can kind of see everything all in one place.
Okay, great. Is this an extra mic?
It is, but we would prefer.
I'll sit next to the mic, so if I'm reading questions.
Sure. Yeah, that would be great.
That way.
You know what? Just take that one. I'm not gonna use it. So just keep it with you, and then that way we can keep that mic as is on the stand, just for anyone wanting to get up, and then you can just kind of babysit that one.
So this looks like it's on.
Test.
Okay. Oh yeah, of course. There you are, Caitlin. Yeah, of course. Yeah, of course. No, hey, no problem at all. All right, I think you should be good now. That's the yelling happened when you were yeah, you were just yeah.
Was everyone able to test the remote?
Except for checks.
I guess is everyone online? Maybe it's the first order question.
Let me go back to the run of show real quick. So I'm only missing Hong Zhang.
Oh, okay.
He's the only one I do not see in here yet.
Okay.
Make sure though that he hasn't been admitted while we were talking. It doesn't look like he is here yet. He wouldn't possibly be.
Your voice echoing.
Test.
Thank you all for joining us for the cross-working group session on parameter estimation for uncertainty quantification, calibration, and process understanding. There's going to be a little bit of AV switching back and forth here, so just bear with us as we get into this. My name is Linnea Hawkins. I am co-organizing this session with Katie Dagan, Margaret Duffy, and Claire Zarakis, as well as Trude Eidhammer, who couldn't be with us today as it's, I think, 2 a.m. in Norway or something. So I'm going to give a little bit of logistics before we get started. We're going to have 6 10-minute talks with 2 minutes for questions, and we'll follow that up with a 30-minute open discussion. We'll be monitoring the chat, so folks online can ask questions in the Zoom chat, and then folks in the room can ask questions at the mic in the center aisle. We want to just encourage during the Q&A session and also during the discussion that we engage in a respectful and constructive dialogue and make sure that we also share the air so that we can hear a diverse perspective from a range of different folks in the room. And then there's no scheduled break, so yeah, feel free to move around. I know it's been a long day. Okay, so before we get to our contributed presentations, I'm going to give just a short introduction to the focus of this session, and then Katie and Claire and Margaret are going to give an overview of some ongoing parameter estimation projects and work in CESM. So efficient and accurate model parameter estimation is a challenge that's shared by all of the working groups. And while we've always had to adjust model parameters and calibrate our models, there's sort of been a recent renewed interest in these questions around parameter uncertainty. And from my perspective, I see that as attributable to a confluence of recent scientific advancements. First, I think we've increased our computational capacity such that we can now generate these larger perturbed parameter ensembles where we strategically adjust parameter values in the model. And you'll hear those referred to as PPEs throughout the session. We're also seeing just rapid advancement and expansion of Earth observing networks and satellite observational products, but they're also becoming more accessible and available due to cloud storage and computing, and that's been really valuable to these types of efforts. And then lastly, machine learning is really emerging as a valuable tool for these high-dimensional, data-driven problems like parameter estimation. So given all these advancements, I think we're seeing many groups at NCAR start to exploration of model parameters. And so our hope is that this session will be an opportunity to bring those groups and efforts together so that we can share knowledge and experience cross-working groups and collectively advance our methodologies. So I want to just quickly speak to some of the applications where we see parameter estimation as being valuable to the CESM community. First, parameter estimation plays a fundamental role in model development, but as we start to bring in new parameterizations, specifically machine learning-based parameterizations, we expect that these tools will be more valuable. And then also as we start applying our models at different resolutions, high resolutions, variable resolutions, having quick and efficient parameter estimation will be key. Second, in actionable science, we heard a lot about applications in the last session, but being able to calibrate a model quickly for a specific region, a specific domain, at a time scale of interest, will make CESM more of a deployable tool for these actionable science applications. And then also as we move towards a more unified model architecture, we'll need to maintain a hierarchy of model complexity. And so having tools to calibrate and estimate parameters for different modes or for coupling different components, or having application-specific configurations of the model, again, these tools will be valuable. And lastly, just quantifying and constraining uncertainty, helping to guide our model development and constrain projections. So I just want to highlight that there are many efforts ongoing at CESM that are using these tools and developing these methods. There's the CAM PPE, CLM PPE, and coupled PPE, which we'll hear about shortly, but there's also efforts in hydrology and paleoclimate and data assimilation, and we'll hear about some of those ongoing projects in this session, but I think there's more, and I'm hoping that we can find out and bring together these groups and really work towards these goals together. And then I also just want to highlight that there are several other talks throughout the next couple of days that are very related to these questions as well, in both Tuesday mornings, atmosphere, land, and ocean model working group sessions, and in Wednesday mornings, biogeochemistry session. So to me, seeing this range of applications really exemplifies the diversity of how these tools can be applied, right? They're not just for model development or calibration, but you can also use these tools to ask science questions and improve our process understanding. So with that, I'm going to hand it over to Margaret, who's going to give us an overview of the CAM PPE.
Hello. So I wanted to just briefly introduce the CAM, so the atmospheric models, perturbed parameter ensemble. And let me just start by saying that I'm actually really presenting on behalf of Truda Eidhammer, who ran these before I even started at NCAR. So this is an ensemble of 263 simulations, and these simulations differ in 45 different atmospheric model parameters, each of which relates to cloud processes in some way. So I have this little schematic on the screen which shows the various processes that are perturbed, whose parameters are perturbed in this PPE, and these come from the convection, microphysics, aerosol, and turbulence schemes. These are 3-year atmosphere-only simulations with fixed SST run with CAM 6.3. I think we haven't seen a little schematic of Latin hypercube sampling yet this session, and so I thought I would just put this kind of 3-variable example up on the screen. This is, again, a slide from Truda, and what we can see here is that there's 3 parameters that are being varied all in conjunction with one another, and you probably cannot imagine what this would look like with 45 parameters, but that's what we've done. And then on the right here is the distribution of each of these 3 parameters, and we can see that when we use this Latin hypercube sampling technique, we're sampling the parameter space relatively uniformly. Okay, so I mentioned 263 of these simulations, all perturbed with 45 parameters, all perturbed kind of in conjunction with one another using this Latin hypercube sampling. And for each of those 263 simulations, we have 3 different experiments. So a present day kind of control simulation, a PI, and an SST4K. And so differencing PI and PD can give you a sense of what's going on with the aerosols, and differencing SST4K and PD can give you a sense of what's going on with warming. I also wanted to point out that this data is available, and there's a URL and a QR code on this slide, but you can also contact us if you were interested in using the data from the CAM PPE. And there's just one final note that I want to make, which is that we actually have there exist really two versions of the CAM PPE. And today's talk by Jiang will include some information using this paleocaliber version of the CAM 6 PPE. And this differs from the sort of original version in a couple of ways, but primarily that it's tuned to paleoclimate evidence. And so we can see in this schematic on the left that this sort of climate calibration has reduced the climate sensitivity in this model, in this version of the model, and so there's also a PPE with this paleocaliber lower climate sensitivity version that you will hear about today. And so that's all for the atmosphere. I will pass this over to Katie to talk about the land.
Okay, so yeah, we wanted to also introduce the community land model, PPE, Perturbed Parameter Ensemble. This is a project that includes a number of us across NCAR and the university community. We've been working on it for a couple of years now. We know that the land model has a lot of different processes that it's trying to represent. So this is the schematic in the upper right. But when we actually went to sort of discover and map all the parameters, we found that there were over 200 of them. And so this is sort of the bar chart that Daniel Kennedy made in the bottom left here. So we thought, okay, these parameters are all across different processes in the model. They've sort of been looked at maybe on their own in different simulations, but what if we tried to sample all of them? And then so the next question was, okay, how do we actually do this? And this is what we've been working on as a large community effort to kind of figure out how to sample such a large and complex parameter space. So our roadmap included first identifying and defining the parameters, over 200 of them. Also, even discussions about what is a parameter versus a structural constraint in the model. Some kind of interesting questions there. Logistically, how we did this was we created a Google spreadsheet that the community and all of our sort of members of the team had access to, where we were able to populate information on these different parameters, what parts of the model they're in, what their lower and upper bounds were, if there's any references that we have for them. In the land, we also have the added complexity of parameters that vary by plant functional type. That's the PFT abbreviation that you see in the spreadsheet. So this was our way of sort of tracking this very sort of complicated space. But we also needed to do things like infrastructure development. So how do we sample the parameters? How do we generate these large ensembles? A lot of work in computational efficiency. Being able to do fast spin up on a sparse grid is something that we experimented with CLM. And so the first ensemble that we ran is a one-at-a-time perturbations with all 200 parameters, but we also did 6 different forcing scenarios. So things like low and high CO2, low, high temperature. So that adds up to 2,400 simulations that we have available for the community. And as you'll see on the next slide, a lot of folks are using these simulations, which is great. And then so if we want to sort of drill down further and work towards parameter estimation, we have to think about going from this very large 200 plus parameter space. We do some parameter selection based on some variables that we're interested in, thinking about different metrics. On the land, we're also interested in biome diversity, and of course these environmental perturbations, which are showing us like which parameters matter in low versus high CO2 climates. And so we've run another ensemble that samples a subset of these 200 parameters all at the same time. So then we get the parameter interactions. And the way this works is we're focused on a particular calibration target. In this case, we started with leaf area index. And this is something that Lenny has been working on. And also Daniel Kennedy is going to talk more about this subset ensemble during a talk in the BGC working group on Wednesday morning. So please tune into that if you're interested. And then I also wanted to point out that there's diagnostics available on this webpage, and I'm sure these slides will be made available to everyone. And also the code is on GitHub. So we're really trying to build this in an open science framework. Okay, so again, I'm not going to talk about the science specifically, but I just want to highlight all of the sort of spin-off projects that have come out of the CLM PPE. There's probably more that we're missing from this slide, but we're really excited that the community has been able to use, especially the very large set of over 2,000 simulations that we ran to sample all the parameter uncertainty in the land. And one of those is looking at the coupled land-atmosphere interactions. And so for that, I'm going to turn it over to Claire to highlight that project.
Thanks, Katie. So I talked about this project in more detail this morning. So instead of sharing some results from this coupled PPE project, I wanted to talk a little bit more about the process and some ongoing work and kind of broader questions that we have to think about when trying to understand parameter uncertainty in a coupled context. So as Katie mentioned, there were tons of spin-off projects from this CLM PPE project. So I wanted to highlight a few aspects of this project that made it so easy to kind of initiate science projects using that framework. The fact that there is just a list of parameters that are included in CLM and defined parameter ranges by this community, as well as the modeling infrastructure for scripting ensembles and accessible model output was really, really helpful for kind of lowering the barrier to entry. So I think that's something we should all keep in mind as these kind of comprehensive PPE projects are becoming more popular. And I think this also points to the value of these kind of ambitious community or NCAR-led undertakings, since it really makes it easier to do science questions based on that. So using this data set that we generated, looking at how land parameter uncertainty impacts climate, I showed some results this morning on how the mean climate is sensitive to land parameter choice. We're also working on how land parameters influence summertime temperature variability and the drought intensification process. And we think that there's a lot that we could do with this data set. It's like 5,000 years of output across all the ensemble members, and there's probably more to analyze than we have human power to do. So if you're interested in collaborating or using this data, please get in touch. One of my big takeaways from this work is that thinking about parameter uncertainty in a coupled context is really challenging. So I think a question that we kind of got into earlier was how do we calibrate parameters if parameters' impact depends on the model configuration and the coupling between different components. So I wanted to advertise Amy Liu's talk in the BGC session tomorrow. I think it's a really good example of some of these challenges and how parameters' impact really varies across model configurations. But on the flip side, I think that thinking about parameter uncertainty in a coupled framework also presents a lot of opportunities. So thinking about how we can leverage existing PPE efforts to understand the implications of parameter uncertainty across components. So I think a lot about how land uncertainty impacts the atmosphere. I think that CAM PPE could really be leveraged more to think about how atmospheric uncertainty impacts the land and the ocean. And then more broadly, I think trying to understand parameter uncertainty in the context of emission scenarios and what we as kind of a carbon cycle community have to contribute to that space is both a challenge and an opportunity. And I think that'll be discussed in more depth at the BGC session on Wednesday. So with that, I think we're going to transition to an online speaker. So Duncan Watson-Paris from UCSD is going to be our first contributed talk. Might take a moment to transition. Yeah, but I think he needs to share his screen, right? Yeah. Okay, great. Quick.
Turn on his camera. Go back there.
All right, that looks good, Duncan. You can go ahead and take it away. We've got 10 minutes with 2 minutes for questions.
Okay, fantastic. Thank you very much, and thanks for the introduction. I can't seem to share my video, but I am here in the ether. I want to briefly introduce you to a community Earth system emulator, which I think could be valuable and useful for uncertainty quantification and calibration. I think the introductory talk gave a really nice introduction to the various different ways and use cases for these kind of tools, and building on the ensembles that were described with CESM. The particular kind of uncertainty I'm interested in kind of calibrating and reducing here, I guess, is the model uncertainty, which certainly for near-term projections contributes to a large proportion of fractional uncertainty in global mean temperature projections in future scenarios within the CMIP6 ensemble, at least. Actually, if you look at other variables, for example, aerosol optical depth, that model uncertainty remains important even to the end of the century. And that's largely to do with the parameterizations that have already been discussed, subgrid parameterizations for aerosol, clouds, and other schemes within these large complex models. And so that's the context in which we introduced this Earth System Emulator, ESM. And it builds on previous work we've done of building a kind of data fusion tool, if you like, called the Community Intercomparison Suite, which enables you to easily bring model data onto the same spatiotemporal sampling as the observations, which is often the first kind of stumbling point when you're looking to use these observations to calibrate model data, is how do you do that in an apples-to-apples way. But having done that, then ESM allows you to build emulators and validate those emulators in an open source Python framework that includes tools for inference and calibration, which I'll describe through this talk. So if we think about exploring parameter uncertainty, and we've already heard some of the examples of ensembles that explore that uncertainty with CESM. We kind of take a slightly more abstract view for a moment. We can think of CESM and other climate models as some complex function F, right, which has a number of inputs, the forces being one of them, so the emissions of greenhouse gases and aerosols, and a lot of parameters. So the atmospheric PPE has something like 45 to 50 parameters. I hadn't realized there was a 200 parameter land PPE. So, there are lots of parameters in these models, and they all generate a huge amount of output Y. And what we'd really like to be able to do is take observations of that output, YO, which is often a subset of the full cube of Y. We'd like to be able to do this inverse, right? We'd like to ask what parameters would make the model output something that looks like the observations. Now, in principle, this isn't tractable, or in practice, this isn't tractable. And so, you can frame this probabilistically, and I can write down Bayes' theorem here, and that looks fine. But the difficulty is in this term here, in the likelihood, and the fact, again, that this is not generally tractable or even calculable. And so we turn to a set of tools known as likelihood-free inference. And there are a number of those available, and there are actually some quite recent additions to that family of tools. But for our purposes, I'm just going to focus on a really simple one, which even I can understand. So I'm going to walk you through it on this slide. And it's called approximate Bayesian computation in some literature. I just call it, it's commonly referred to as rejection sampling. And really all it involves is you draw a set of theta from your prior. So this is a Bayesian approach. So you need a prior of your parameters, even if that's a very broad prior. You run those forward through your model to calculate some output y. So this is this step here. And you accept that set of theta if the distance between the observations and the model output is smaller than some small number, epsilon. Now, if that epsilon is big, then you can see that we always accept theta, and then we're just drawing from our prior. But it can be shown that as epsilon tends to 0, this process generates samples, this should say, from this posterior. This is exactly the thing we're after, the probability of that set of parameters given our observations. Now, there are a number of nice things about this. The difficulty is that it's computationally expensive, right? If we want to do get a dense sampling of our posterior, then clearly as we make this small, then our acceptance becomes small, and we're generating lots and lots of these forward models, or sorry, sampling many of these forward steps in order to get a dense sampling of our posterior. And that could be hundreds of thousands or even millions of samples. And so in practice, what we do is use an emulator here approximating our forward model in this loop. And so that emulator enables us to efficiently sample these, to do that forward operation such that we can sample from our posterior. Now this row here, this distance, I've somewhat swept under the rug. There are different ways of doing this. There's a kind of implausibility metric that some people have used, and that goes back to this paper by Vernon et al. In 2010. And that really is just a standardized Cartesian distance. It's the distance between the observations and the emulated predicted output for that set of theta, standardized by a sum of variances. So we have an uncertainty due to the emulator, uncertainty from our observations, and also potentially an estimate of our structural uncertainty. So the remaining uncertainty that we don't have, that we're not exploring through this parameter space. And then we can, use some rules of thumb and say, okay, well, in this case, epsilon, if we set epsilon, which is I here, to be 3, then what we're doing in practice is ruling out any parameter combinations that are 3 sigma away from our observations. And if we do that, that gives us a kind of robust and transparent way of predicting or calculating this posterior. There's a bit of a trick in the fact that as you go to high dimensional outputs or conversely many observations, this Cartesian distance becomes quite difficult because you rarely get observations that always match the model output. So this is the curse of dimensionality, and there's some ways we have to get around that. But if we take a more concrete example, here I'm exploring a three parameter PPE. We explored the emissions of a particular aerosol species, black carbon in this case. One of its optical properties, a gross atmospheric characterization of that aerosol, so that the absorption aerosol optical depth, for those of you who know it, but it's really just a coarse measurement of the absorption of the aerosol. And then there's another parameter, which is the removal of the wet removal of black carbon, which I'm not showing on this plot. And we sample that using Latin hypercube sampling. Thanks for the introduction. Just using 30 or 40 full model simulations. They're nudged, so they're only 1 year each, so it's relatively cheap to do that. But in order to do the full exploration, we still need to fill in these gaps, and that's where we fit our emulator. So the emulator is really just a regression model over this training data. In this case, it's a Gaussian process regression, but in principle, it could be any regression model that allows you then to sample any given combination of these theta. And then once, sorry, I had an extra slide here just to point out that, on that example, these were one-dimensional outputs. In practice, you can emulate whole fields of AA and D. That's not a problem for the regression component. As I mentioned, for the calibration, it becomes a bit difficult, a bit more nuanced. But once you have that, then you can do this rejection sampling, and we just draw, as I say, from our prior. And if the parameter combination gives us an emulator that's close enough to our observations, it gets a green dot, and if it's not, it gets a red dot, and then we reject it. And after enough sampling, after a few 100,000 or 1 million samples, we start to get some interesting structure in our posterior here, which I don't think I have time to go into, but allows us to start narrowing down parameter combinations that gives us models that are close to the observations. I just wanted to, just to say that sampling was actually slowed down for the purposes of this talk. The calibration, the ABC sampler in ESM is built on the same TensorFlow foundation as the emulators, so that this sampling actually happens on the GPU. So the rejection sampling, it's drawing samples from our emulator as quickly as it can reject them. So you can get very fast inference times for these pipelines with this tool. And this scales to many parameters. As I say, in the atmospheric cases, we've looked at 30 parameters and now looking at 50 parameter ensembles. And we've used these to constrain the first direct effect of aerosol forcing and also the first indirect effect in some recent papers with good success. I briefly wanted to show what's involved in setting this up on Jasper. So this, sorry, Casper. So if you have an account on Casper, you can just pip install ESM. There's a little bit of just, for the sake of transparency, this is all the code I use to generate these calibrations. You read in the data directly from the CGD project where the CAM PPE is, and you do a little bit of stuff just kind of reading in the parameters. That's all fine. You put all the PPE members together, normalize the parameters, and then do a test train split, and that's it, right? And once you've done that, you ask ESM to make your Gaussian process model, you give it the parameters, you give it the output, you train it, and then you ask what the prediction is on the test set, and you get an emulator. And having done that, this is it, last slide. Having done that, then you can just say, okay, if my observation is this number, find me all the parameter combinations that match that observation. And so the gist is available here if you have the slides, and you can go and run this on Casper and play with these tools. So hopefully I've given you an introduction and overview of ESM and what it can do and enable some of these really powerful pipelines that build on the wonderful investment that the PPEs have already made in exploring these parameter combinations. So I'll leave it there and happily take any questions. Thank you.
Thanks, Duncan. This is a really valuable package. I use it daily, so appreciate it. And we have time for one question.
I didn't hear the question at all. Sorry, you'll have to repeat that.
I think you have to turn the mic on. Thanks for bearing with us with these AV issues.
Sorry, can you hear me now? Oh,
yes, thank you.
Yes, so it was just a question about actually doing the Gaussian process regression, how you're overcoming the challenges with Gaussian process regression with many samples and high dimensionality.
Yeah, good questions. I probably don't have time to go into all of that, but so we build on well-founded open source Gaussian process. So I don't kind of reinvent the wheel. We use GPFlow underneath, which is a TensorFlow implementation of a Gaussian process regression library. There are techniques, sparse sampling techniques available for building those GP regression models. Actually, in practice, we don't have enough data samples for that to become a problem. So even the couple of hundred samples that we have in the CESM ensemble scales perfectly well with the GPs I've built. Regarding your question of dimensionality, it depends very much on whether you're referring to the output dimensionality or the input dimensionality. And there are ways around each, but I agree it's not. It needs a little bit of thought. We also explore in the package. We have other tools. You can build a random forest or a neural network, but I think they don't give you the well-calibrated uncertainties, which are so useful for the posterior, for the calibration. But I'd be happy to chat more offline.
Thank you, Duncan. So why don't we change over? Our next speaker is also online. We have Hyungshang Yan from the Pacific Northwest National Laboratory. Go ahead and share your screen. All right, we're seeing your screen, just not in presentation.
How about now? Can you hear me?
Screen looks great. Take it away.
Okay, thank you. This is Hong Xiao from PNL, and I'm very excited to report some of our progress on the large ensemble diagnostic evaluation of the hydrologic parameter uncertainty in the CM Model 5. This is a large team effort from collaborative, also from Colorado University and also from UNCAR. This is my storyline of the presentation. I focus on the three objectives. First one is benchmark the performance of the CM Model 5 based on the default hydrologic parameter. So this question is about now. So are the baseline deterministic parameter and stream flow prediction acceptable? The second object is about characterize the effects of hydrologic parameter uncertainty on the stream flow prediction. So this is about how. How is the hydrologic parameter uncertainty shaping the model stream flow prediction? And third part is perform a global sensitivity analysis to evaluate which the parameter most influence the pseudo-diagnostic hydrologic parameters. So it's about why parameter uncertainty is important. So we provide diagnostic assess which parameter process control key features of stream flow prediction errors. Our study area is based on the natural flow basins. We configure the CL Mod 5 from the coldness domain 180 degree cell to the basin scale. We select 464 camel basins. It's all natural flow basins, the highest quality basins over the coldness to represent different hydroclimate regions. We will also classify the basin into 7 clusters using the machine learning, the reproducible k-means clustering. So in this map, you can see cluster 1 is the orange color in the northeast, cluster 2 the Pacific in the west coast. So why we do the clustering? Because we not only focus on the basin scale, we also want to take a look at the regional scale. In total, we consider 27 diagnostic error metrics on the stream flow prediction. On the table on the left, you can see all the 27 metrics. I don't go to details here, including different daily scale, different temporal scale, daily scale, monthly scale, or seasonal scale, or different flow regime. And they focus on such as high flow, low flow, or water balance, or multi-object metrics. So why we consider so many metrics? So because most of the literature focuses only on 1 or 2 error metrics. So because different metrics can ask different questions. For example, if you focus on the hydrological drought, that's our project focus on the hydrological drought. So you need some metrics focus on the low flow, such as the low flow regime bias or the daily transfer root mean square error. But for some other applications, such as reservoir modeling, water resource management, they focus on the annual scale or monthly scale. They focus on the water balance. So you choose different metrics. And last, if you are a flood management engineer, you focus on the high flow. So you should choose the daily scale or even hourly scale to get the highest peak flow. So let's take a look on the first object, the default parameter performance. So this picture shows the default parameter performance using the KGE metrics. We can see strongly regional difference in the daily flow KGE from a 10-year period. For those of you who are not familiar with KGE, so equal to 1 is the perfect model prediction, higher than 0.7 acceptable. 0.5 some modeling scale, if it is negative, means it's very poor performance. The higher the red color, the better the performance. So we can see quite a regional difference especially on the coast area. You can see such high performance scale, but in the central or in the Rocky Mountains, you can see little worse performance. But also the performance vary in different time scales. So not only focus, you change your temporal scale, you can get totally different answer. Let's just use one basin as an example in cluster 1 in North Carolina. So if you take a look on the daily scale, the NSE value is lacking. It means a very poor performance. But if you aggregate flow to monthly scale, you can see, okay, our model is very well on the reservoir modeling, but it's not good for the flood management application. So that's why you need to have multiple diagnostic metrics to get a full picture. And also on the water balance, they show quite strongly regional difference. On this picture, different color means different cluster, like blue color is a cluster 2 Pacific. On the X label, you can see different temporal scale from annual scale to seasonal, winter, spring, summer, fall, or different flow regime from low flow regime to the high flow regime. So just use the blue color, the cluster 2 Pacific, as an example. You can see the default parameter give a very good water balance. But if you focus on the drought application, because the drought is in summer in Oregon State and Washington State, you have a significant underestimation of flow, and things you can find out on the low flow regime. So even you have a good annual water balance, that does not mean you have a good low flow simulation, does not mean you have good high flow simulation. So the second part is about characterize effects of parameter uncertainty on the stream flow prediction. So in total, we use the CM model PPE version. We work with our NCAR collaborator to identify 50 hydrologic parameters, including all the hydrologic process, including surface, subsurface flows, soil canopy evaporation, and we draw 1,500 ensembles. As a total, we have 700,000 simulation for the 10-year period in all the basins. Okay, here's a picture showing the parameter uncertainty on the mean annual flow. This picture showing the coefficient of variation, that's a standard deviation divided by mean. It's a measure the dispersion of the ensemble prediction. So the higher the value, you can see the larger the spread of the ensembles. You can see quite regional difference on the CM model. Much lower spread in the coast, also on the Rockies, but in the central US, Great Plains, you can see a much higher spread. And also we take a look on the shape of the flow regime. On the X label, you can think about this from low flow to high flow, and different plots showing different cluster from cluster 1 northeast to cluster 7 southeast. And Y label showing the monthly flow shape. You can see that for different regions, the shape is different. For example, in the cluster 5 Great Plains, you can see the spread is quite similar from the low flow to high flow. But if you move to Pacific, you can see they have a much larger impact on the low flow than the high flow, the parametric uncertainty. But I want to point out, even for the 99% quantile, the high flow, the parametric uncertainty have a 46% related difference on the stream flow prediction. I did some studies on the Pacific regions. When consider climate change impact under the RCP 8511 at the end of the century, they have similar magnitude impacts on the stream flow prediction. That means the parametric uncertainty have very similar impact on the climate change impact uncertainty. This slide showing the behavior parameter. So we have a large ensemble. Can we constrain this ensemble using observation flow? Yes, we can. Not only one constraint, you can add multiple constraints. For example, the blue showing the observation. So the red color showing the observation, the blue color showing the default simulation, and the green color showing the prior range of all the ensemble. So in this plot, you can see what the default parameter simulation, what the observation, and what are the ensembles. And blue color and this pink color, they have a 1 metric constraint and 2 metric constraint. If you take a look at cluster 5, you can see that the pink color have much more constraint close to the observations. But in the meantime, if you take a look at the cluster 2 Pacific, they don't have 2 metric constraint parameter. That indicates some model inadequacy in simulation that's low flow, especially compared to the observation here. Similar finding on the cluster 4 Rockies. So the last one is showing the global sensitivity to evaluate the parameter on the hydrologic metrics. So this picture showing the sensitivity score to monthly root mean square error. Focus on high flow error. So just use one matrix as an example. X label shows all the 15 hydrologic parameters, Y label shows each basin in each cluster. And different picture were showing for different metrics, of course. But in here, you can see quite regional difference, like cluster 1 northeast, cluster 2. You can see the surface parameter dominate on the high flow simulation. But if you move to cluster 6 Great Lakes, you can see the soil porosity dominates. This parameter dominates all other parameters in the high flow simulations. So this results can be guiding to model calibration and provide model diagnosis. I take a look, I find the soil depth in cluster 6 is very deep. So that's why it dominates this high flow simulation process. Last, I used just one cluster basin as example to see how this sensitivity can help on the model calibration. So if I focus on the low flow drought applications, I find the two parameters. First one is the canopy parameter. The second one is surface water parameter. Then we can have a scatter plot on the what is the low flow volume bias here. Then we find the top 5% partition. There's a behavior parameter. It's quite interesting to see the linear separation because it's not common to see the linear separation. So you can take a look on the prior rate. The bias, the prior rate is very large, but if you have the parameter constraint, you can have a much close to the zero bias, the behavior, the parameter, and they can help to produce enhancements ensemble stream flow prediction for drought study in this basin. Okay, this is my last slide. I will stop here. And all the M3 project is open access, including the publications, the data set, and all the data set are publicly available in this repository. We're not only including 1%, we're including 5% to capture the force uncertainty, also compared to parametric uncertainty. And this is an upcoming presentation tomorrow by my colleague. Thank you.
All right, thank you. I think maybe we could have time for one question while we change over to the next presenter. So if you could unshare your screen. Well, I appreciated the emphasis on how you can get different results for different calibration metrics, and highlighting that I think is really important. Over to our next presenters who are joining us from Google. We have Rob Van Baren and Aaron Sonnenbend. So you can go ahead and share your screen.
Okay. All right, can folks see and hear me?
Okay, but the screen is not sharing. Can you maybe retry?
Yeah, let me do that again. I promise this worked once.
It's just the story of this session.
Okay, how about now?
Still not. Give us a minute.
Okay. Yeah, on my side, it says that I'm screen sharing for whatever that's worth.
We're just gonna have to do that.
Does that work for you? Sorry, Rob. We're going to have to share your slides from our screen, and then I can advance them for you. Does that work?
Yep, that sounds great.
Stop sharing your screen, please, Rob.
Yep. Okay, stopped on my side.
All right, we're all set up in the room now. Thanks for your patience. Sorry about that. And
Okay,
just let me
great.
know and I can advance.
Yeah, no worries. Thanks for the help in getting everything set up. I know that's could be a challenge. All right, so hi everybody. I'm Rob Von Baron. My collaborator Aaron Sonnabend and I are part of the climate and energy team inside of Google Research. Aaron unfortunately can't join us today. His wife just had a baby this morning, so I'm going to be channeling him for the last part of this talk when we talk about the stats aspect of it. Go ahead and go next slide. So just a brief overview of what the climate and energy team does. Our role inside Google is to try to understand what kinds of projects it would make sense for Google to help contribute to, either through computation resources, through scientific explorations, or potentially financially. So one of the things, of course, that we'd like to be able to figure out is which kinds of projects are better to invest in, and to the extent that we can understand different kinds of climate mitigations through simulation and say make statements about one being better than another, that's a helpful thing for us to do. We do have some challenges running this kind of stuff on our side and using CESM. In particular, we don't have access to the same kind of dedicated cluster environment that a lot of folks do, and I'll talk about that in a second. And of course, then there's the big challenge that everyone's talking about today in this session, the uncertainty in CSM. Next slide. I don't know if it's switched on your side. Okay, there we go. Thanks.
All right, thanks. Could you
So,
just speak up just a little bit? It's a little quiet in the room.
I'm sorry, what was that?
Could you speak up just a little bit? It's quiet in the room.
Oh, yeah, I will shout at my screen and hopefully that'll work better for everybody.
Thank you.
So just briefly, the infrastructure that we have available on the compute side, the best price for performance that we can get is to use preemptible VMs on Google Cloud, which means that we have to tolerate failures of nodes basically at any time. This doesn't work very well with MPI-based multi-node simulations, so we're really focused on doing single machine simulations. That means that the kinds of simulations that folks often do, at least for atmospheric science questions that we've been looking at, where they'll do a run to equilibrium simulation going for maybe 100 or 150 years. That doesn't work particularly well because I don't have the patience to wait around for multiple months to finish one simulation. So instead, we've been looking at wide simulations where we're running a large number of simulations for a short number of years each, similar to what some of the other speakers have been talking about with parameter estimation. And as others have obviously noticed too, this is a pretty nice platform for doing this kind of exploration. So in our case, it's pretty easy for us to get hundreds or thousands of VMs spun up at the same time. So we can do a lot of different simulations at once, but running them for many simulated years is a little labor intensive and takes too long. Next slide. One of the things that we've been exploring is the impact of airplane contrails on the climate. Lots of folks, of course, have looked at what the impact is in terms of the radiative forcing. We've been trying to examine what the error bars on that impact are. And for this talk in particular, focusing on what kinds of mitigation strategies might work and be the most effective. Next slide. So to give a quick idea of the simulation setup that we've been focused on, we're using CAM 6.3 with fixed SST. And we typically run 3 different scenarios. We'll run a no aviation scenario, so the baseline case with no air traffic, a full aviation scenario where we turn on aviation and we allow the built-in CAM contrail module to work. And a hat tip to Andrew Gettleman and Jack Chen, both for their work on the contrail module and for helping us get set up with using it. And then we'll run a mitigation strategy scenario where we turn off aviation traffic for some portions of the day to simulate what would happen if we were able to direct airplane traffic through areas where they're less likely to create contrails. And then we'll measure the top of atmosphere radiative imbalance and compare that across scenarios. So you see on the right a couple of examples of simulations we've run. These are with either 50 or 400 ensemble members for each of the cases, depending, and then averaged across the year. So you get an idea, with the red being places where contrail warming is the most significant, and blue being where the model shows some amount of cooling. And the bottom shows a mitigated case where, fortunately, all the numbers are smaller, so that mitigation seems like it's helping, which is good. And just to give an example of the scale of computation, over the last 4 months, while we've been focused on this particular study, we've run about 83 ensembles of 50 plus members each, and done about 10,000 simulated years through CSM. Next slide. So examining the error bars on contrail ERF, obviously there's both the aleatoric uncertainty that you get from the variation amongst ensemble members and the epistemic uncertainty from different parameter choices. And as you can see with the graphs on the right, some of these parameter choices have a pretty big impact on what the output is, not surprisingly. Next slide. Ultimately, at least for the purpose of this talk, we're going to focus on how we can understand the mitigation effectiveness. And so one way of doing that would be to just go parameter by parameter and do ensembles for each parameter choice and look at how effective that is. So this is an example of that strategy on the right. Each little X represents a 50-member ensemble where we've run for a couple of years, and then we can compare the mitigation strategy to the full air case. Pardon my automatic light, trying to make sure we're not using too much electricity in the house. And then, of course, the problem with that is we spend a lot of computation to do many ensembles for every parameter combination. And it's not really obvious what we do to compare these things. There's a clear gap in the behavior in some cases, but other cases they kind of overlap. And what do we do with that? Next slide. So the solution that we've been playing around with, and this is kind of work in progress, is to use Monte Carlo sampling of the parameter space and then run that through CESM to get TOA values and use analysis of variance to actually understand both the effect, the experimental effect, and to examine the mitigation. And specifically for evaluating the mitigation, we're looking at the mitigation ratio, or the effect ratio rather. So to compare the full air effect versus the mitigated effect. Next slide. So to make this a little bit more concrete, the first thing that we do to set this up is and hopefully people can see my mouse as it's waving around. We generate a Monte Carlo data set by sampling parameters from a distribution that seems reasonable for that parameter set, augmenting the set with a full air indicator function. So it's either 0 or 1 based on whether or not we have aviation turned on. And then we generate TOA values from CESM to create this Monte Carlo data set. And we're modeling this with a fairly simple statistical model where if we kind of parse things out a little bit, the important things to pull out are beta 0 is just the baseline bias in the model. So this is the no air TOA value on average. Beta 1 is the full air effect. And we can see that as long as we keep the expected value of this G function, which is the kind of nuisance function that absorbs the variation due to the parameter changes, as long as the expected value of that is 0, then that will factor out when we take the expectation over the different parameters. And we're just left with a simpler piece here, which we can use to factor out beta 1. So that's the statistical approach we're taking. Next slide. And just a quick intuition for how this would work. So if we pick particular parameter values shown with the circles up top. That will give us particular distributions or density functions for each of the parameter values, but then we can combine those and factor out the beta 1 here. Next slide. So to take a look at a mitigation strategy, we can employ the similar approach on the statistical side to create a model and factor out alpha 1, which would be the effect of the mitigation strategy. And this picture on top gives just an intuition for what a mitigation strategy for contrails might look like. So since aviation contrails have both a warming and a cooling effect during the daytime, because the clouds, as they're covering the Earth, will reflect incoming solar radiation, but also blanket the Earth and reflect outgoing long wave radiation. During the daytime, the effect seems to be lower in general. This has been stated in other parts of the literature. At nighttime, the primary effect is warming, and so what we've done is looked at a mitigation strategy where we turn off contrails starting 3 hours before sunset, and then we turn aviation back on 3 hours before sunrise. Next slide. So using this statistical framework, we're able to isolate alpha and beta and compute this alpha over beta ratio that shows the effectiveness of the mitigation strategy. And just to kind of give a more concrete example of how we would run this in practice, once we've done Monte Carlo simulations for both the full air and the mitigated cases, then we can sample with replacement from those Monte Carlo data sets to create estimates of alpha 1 and beta 1, and then use those estimates to create estimates of the ratio along with confidence intervals. And so this example, the graph on the right, is using some simulated data based on parameters that seem to characterize the distribution well. We haven't run the full Monte Carlo simulation yet because we're still trying to get better priors on our parameters for the contrail simulations. But if we wind up with something that looks like this graph and the confidence interval is far away from 1, that means that the mitigation strategy warming is far lower than the full air warming, which would mean mitigation strategy works. Next slide. So the gist is that this strategy seems to be a nice way of using the compute infrastructure that we have, because we can do wide ensembles fairly easily. We can run lots of concurrent simulations with different parameters. And as long as we can sit in a regime where short simulations are good enough, which does seem to be the case for this particular case of contrail measurements, then this is a nice technique. And then the variational analysis allows us to make strong conclusions about the mitigation effectiveness in spite of both the aleatoric and epistemic uncertainty. And I'd also point out that a nice artifact of using Monte Carlo simulation and Bootstrap is that we don't need to run large ensembles around each parameter set, but instead can do a fairly decent sized Monte Carlo simulation. From what we've seen so far, on order of 500 ensemble members seems like it's probably sufficient to get good stats. Just probably an order of magnitude less than what we would need to do if we did kind of a more naive approach. And with that, I'm happy to take any questions.
All right, thank you, Rob. We'll take some questions while we change over to the in-person talks.
Great.
Got a question in the room.
Yeah, thanks. I was just curious what motivated the choice of this particular problem, the aviation sector. Was it the shortness of the simulations that you could do to and potentially get an impact, or was there some other?
No, it wasn't. It wasn't motivated by the simulations. Actually, it was motivated primarily based on what we'd seen in the literature around the potential impact of contrail forcing. So work not done by us, but done by many others in the past, suggests that the warming impact just from contrails is maybe equivalent, possibly even a little bit larger than the warming impact of CO2 from aviation. So it's a quite large effect. And it's the kind of thing that seems like we might be able to address by just rerouting planes, having them fly a little lower, for example, where they're less likely to be in a zone that's going to create contrails. So it might be a way of reducing warming at a relatively low cost, and something that we could try to convince airlines would be a good idea. I can't hear. It looks like there's somebody maybe asking a question. I can't hear it on my side.
No, that was just AV tech.
Oh, okay, great.
Rob, if you don't mind, will you stop sharing?
I am not sharing. It was done through the room.
Gotcha. I will go take care of that.
Great.
Well, next we have Jiang Zhu, who's from NCAR. And the rest of our talks will be in person.
Hello, everyone, and I want to thank the organizers for giving me this opportunity to speak. This study is about. Okay.
Check one thing here real quick. Hold please, sorry about that. Testing. Testing.
Okay, this study is about the state dependence of the cloud feedback, and we use perturbed parameter ensemble trying to account for the uncertainty from model physics. Well, this figure is from Sherwood et al. 2020 paper summarizing the estimated equilibrium climate sensitivity from different lines of evidence. And from this, you can see that so far paleoclimate provides the strongest constraints on climate sensitivity. And how does that work? Because from paleoclimate reconstructions, we can estimate the major forcing CO2 here, and also the temperature response. So here we are looking at two time series of the CO2 and global mean temperature change from the pre-industrial climate and over the past 60 million years. So with the major forcing and the temperature, we can compute the climate sensitivity directly. And one major advantage of the paleoclimate constraint is, as you can see here, that we cover a wide range in terms of the forcing and the temperature response. So if we look at the past 60 million years, the warm temperature could be 14 degrees C warmer than the present day, and the cold climate could be 5 to 6 degrees C colder than the present day. So this big signal, big forcing ensures that we have a tight constraint from paleoclimate constraint. However, this wide temperature change also brings in potential problem. For example, we shouldn't expect that the forcing and all the feedback processes stay unchanged during this wide range of temperature change. And in this talk, the question I'm particularly interested in is, does the cloud feedback increase or change with global warming? To show that this is an important question, I use a paleoclimate calibrated CESM tool, which has a climate sensitivity of 4 degrees C, which is much lower than the standard CESM tool. Please check out the paper if you are interested in the model. And to this model, I performed fixed SST simulations, pre-industrial and based on pre-industrial, and with uniform cooling of 4K and the uniform warming of 4, 8, 12, and all the way to 16 K. So this temperature range roughly covers the global mean temperature change over the past 60 million years. And using each pair of SST plus 4K simulations, we can compute the cloud feedback. And in the figure on the right, we are looking at the shortwave cloud feedback from these simulations. As you can see that when we warm the climate, the cloud feedback increases with warming. And for example, if we are looking at a climate with global mean temperature 8 degrees C higher than the pre-industrial, the cloud feedback could be higher than the pre-industrial based cloud feedback by 0.5. This is a huge number, has huge implication. If you plug in those simple numbers into the forcing feedback calculation, this can increase the cloud feedback from 4 all the way to 8. So this has huge implication on the understanding of warm climates. The previous results is only based on one single model, one configuration, and we know that there's huge uncertainty from the model physics, especially regarding the parameterization of cloud-related schemes. That's why we use the perturbed parameter ensemble here, trying to account for the uncertainty from the model physics. We took the PPE configuration from the atmosphere model working group, and we perturb 45 parameters. Some examples are listed here, using 250 ensemble members. And each simulation we run 5 years. We use the 2-degree version of the CAM6 with paleofixes. And we performed 7 suites of fixed SST PPVs. So that's a total of 1,500 simulations. The simulations are pre-industrial SST and minus 4K plus 4, 8, 12, and 16K. So again, those temperatures are designed to cover the temperature variation over the past 60 million years. Next, let's look at the results. So the top panel shows the cloud feedback from the pre-industrial climate state. Each dot corresponds to one ensemble member. We have 250. And the star here shows the configuration with the default parameters. And looking at the cloud feedback, you see that within the single model, our PPE can cover a wide range of the cloud feedback, and the range is comparable from the CMIP6 models. So meaning that we have an efficient way to account for the model physics from our current understanding. Next, let's look at the state dependence. So here, the x-axis is the cloud feedback computed for the pre-industrial climate state. And the y-axis is the cloud feedback calculated from a different climate state. So here, the leftmost plot is cloud feedback for a cold climate state. So I use minus 4K and pre-industrial to compute the cloud feedback. And if all the markers fall onto the one-to-one line, it suggests that we don't have any state dependence. So the pre-industrial cloud feedback is exactly the same as a cold state cloud feedback. That's roughly what we see here. You see the markers are scattered around this one-to-one line. And we have a very high correlation between the two, although the ensemble mean is slightly larger for the cold climate state. How about if we impose a warming? So here's the next plot. If we impose another 4K warming from this already warm climate state, we can again compute the cloud feedback. You start to see that for some of the configurations, the cloud feedback start to departure from this one-to-one line, suggesting the state dependence start to show up. If we keep increasing the temperature, for example, we push the global mean temperature to 8, 12, even 16K, we can do the similar analysis. And interestingly, you see that the correlation between the pre-industrial cloud feedback and the cloud feedback from warm climate states goes to almost 0 in these two cases. So given that the the signal here is relatively noisy, and considering that not all the configurations are realistic, are compatible with our observational and theoretical understanding, what I'm going to do next is to use constraints from present-day observation of cloud forcing, cloud fraction, as well as the expert-assessed cloud feedback from the Zelinka et al. 2022. So when we use all those constraints combined together, the plot here shows the top performed 50 configurations. And focusing on the very warm climate, you see that we start to see a more clear response. So in terms of the ensemble mean, the warm state climate tends to feature higher, stronger cloud feedback, and this increase with global warming is particularly clear if the configuration tends to have a relatively weaker cloud feedback in this parameter space. And you may wonder about the mechanism, what is driving this state dependence. To look into that here, let's first look at the high latitude. I'm plotting similar results, so pre-industrial cloud feedback and different climate state cloud feedback, so only for the high latitude. And you can see that when you cool the climate, the cloud feedback decreases with cooling. And when you warm the climate, the cloud feedback increases with warming. And interestingly, there seems to be a saturation behavior. So that shows that suggests that it's potentially related to the ice amount in the mixed phase clouds. So that's a state-dependent process through the associated cloud phase feedback. So for very warm climate, as you warm the climate, the cloud ice decreases with temperature, and for very warm climate, you don't have any cloud ice, so zero cloud phase feedback. Is, in the end, they reach this saturation. How about over the lower latitudes? We see a relatively noisier results, and you see that for some configuration, the cloud feedback could increase with cooling and increase with warming. So this is non-monotonic behavior. This suggests that likely there are multiple mechanisms at play here. Okay, some take-home message. The cloud feedback likely increase with warming, and we have the ensemble mean here and the range in our PPE. And regarding the mechanism, the high latitude, the state dependence could come from the cloud ice in the mixed phase clouds. So it's a simple thermodynamic process. And for lower latitudes, given this non-monotonic behavior, we suggest that there's likely multiple physical processes at play, and we see a relatively larger uncertainty over this region. So this basically reflects our current understanding, so relatively poor understanding from observation and modeling. So I will stop here. Thank you.
And take questions while I change out the slides.
Check. Okay. Thanks so much for that talk. I really like how you're using this kind of PPE to ask a science question. And so I'm just wondering if there's somewhere you're thinking about going from here. Are there other science questions you can ask with these simulations? Because you've taken the parameters from the CAM PPE, but then you had to run all of these different paleo configurations. So are there other areas that you're thinking about exploring with these simulations?
Yeah, that's a great question. And there are classical questions in paleoclimate, such as the temperature gradient for warm climate. For those questions, we may need to extend to coupled PPE to look into. But with this set of PPE, we can also look into how the convection, for example, precipitation vary over this wide range of temperature. Thank you.
One more quick question. So you alluded to it, you said the PPE configuration are not realistic. So if you retune the model to be realistic for each case, certainly the scatter would drop. Would it also affect the slope and the climate sensitivity if you retuned every case?
Yeah, I think given that the cloud-related parameterization is the most uncertain aspect, I wouldn't take one single configuration like it's very robust. So I think it's great to get the statistics from this PPE ensemble. I'm not sure this answers your question though. Happy to chat afterwards.
Jeff Anderson from NCAR.
Slight change of pace. I'm going to talk about parameter estimation using ensemble data assimilation in particular, with the data assimilation research testbed. So ensemble data assimilation combines observations with an ensemble of model forecasts. It's a Bayesian technique. It's designed to produce forecasts that give you the best possible fit to the observations over a large series of times. It's the method that is used for operational numerical weather prediction, but it is vastly applicable to many other things, inner science and beyond. We're using the Data Assimilation Research Testbed, which recently celebrated its 20th anniversary. It's an NCAR facility to provide a community access to these types of tools. It can be used for both observing system simulation experiments, where you simulate observations from a given model, and that's important to this parameter estimation process. It can also be used for real assimilations, where you're using real observations and trying to make real predictions. And of course, it's important to realize that ensemble prediction, and DA in particular, is really essential to understanding prediction, predictability, and model development, which is part of the context of parameter estimation. Quickly, I knew this was coming. The things that are black are a mix of blue and black, since the red part of the projector has suddenly turned off again. DART works for all of the NCAR models up there. There's some NCAR ones and not NCAR ones, but all of the atmospheric models that are available in CESM, both ocean models that are available in CESM, sea ice, the MPAS component, WACM, WACM-X, chemistry versions of these models, CLM. It works with a lot of other NCAR models too. Again, now the red you can't see, but this is an example of the observations that can be used. Perhaps the most important one here is it can use any currently launched, past launched, or proposed remote sensing instrument in orbit through RTTOV. So it can use lots and lots of remote sensing in addition to just about every in situ observation you can use. So it can compare forecasts to these types of things. So this is a mature system. An example of this is, again, a CESM product. This is a project that was completed by Kevin Rader, who's in the next room right now. So we've done multiple 10-year reanalyses. The most recent one was completed about 2 years ago using CAM6. It is roughly comparable in quality to things like ERA or other reanalyses, but it uses CAM. You can get restart forcing files from CAM for other things, and it is ensemble reanalysis. And so having this forcing files from these 80 members is extremely important to maintaining variability, which is key for these types of estimation problems if you apply it to other components in CESM. And Kevin's available to talk about these things as the meeting goes on if people are interested. There's the name. Okay, so how do we do parameter estimation? So normally when you do data assimilation, you have the model state variables, things like gridded TUVQ, or leaf carbon, phytoplankton concentration, ice area. Okay, pick your favorite model variables, and you compare those to observations, and you come up with the best values for those that give you good forecasts. But back in 2001, we realized that you can also add in parameters to these things. So basically, each ensemble forecast that's used in this now gets its own value of the parameter. And we can come back to the selection of that, which is relevant for other things that have been discussed here. This is called parameter or state augmentation. There's a bunch of challenges here. Parameters don't change. They don't have a forecast model, and that can be important. You have to get a guess for these things to start with, as I mentioned. They're never directly observed. Of course, nothing else is never directly observed either. Model variables aren't directly observed. And there's constraints on the legal values for these things that come into play. So despite these challenges, I'm going to give you some examples here that show some successes, show some applications, and show some challenges too. The first example I'll give was run by one of the team members of the data simulation research section. We're up in CESL. This is by Moha Garamti. He used a derivative of the CCSM4 model called NORWECOM. In particular, he did estimations of parameters in the biogeochemistry part of the ocean model there. The details of this particular study aren't important other than to say that he was successful and able to do this. But the one key point is that in these two panels here, which are a little bit noisy, down on the right part of the thing, you can see a black solid curve and you can see grays around those. Those grays are ensemble members showing you uncertainty. The black is the ensemble mean of two particular parameters in that model. And the key point here is that one of them appears to converge to a value that is constant in time. The other one on the right has a seasonal cycle. And so there's a question of when you're estimating parameters and you want to best fit things, do you want a time constant parameter? Do you want it to be allowed to vary in time, slowly, quickly, whatever else? These are open questions that need to be addressed, whatever your application is. Just a quick note is that we have a current ongoing summer project collaboration between CGD and CESL with a summer intern working on it to allow this type of estimation in MARBLE, the ocean biogeochemical model in CESM. That was not on the previous slide, but hopefully next time I talk to you, it will be. Another example is in CLM. This is part of the solar-induced fluorescence modeling and comparison project. There's a significant model parameter part of this. CLM DART is one of the things, and Brett Ratska will be talking more about this. He was on the list you saw earlier at 10:45 on Wednesday in the BGC working group. Just quickly, another example. So sources going into CAM are really parameters. This is an example of work that was done by a graduate student of Inez Fung's, Stephanie Worth, and she's actually estimating global carbon sources using observations to constrain the parameters that are getting put into CAM. The upper left panel are her results. That's compared to Carbon Tracker, which is one of the state-of-the-art things. And so you can use CAM to do this type of estimation process. Again, this is a parameter estimation process. Now, I think I'm going to show the oldest slide, I'm guessing, in this CESM meeting. You'll notice the date on this. This slide is a direct copy of a slide that was shown in the AMWG in spring of 2005. And this is an ancient model, but the point here is important. We were working with the CGD scientists to try and estimate parameters related to the gravity wave drag scheme in CAM at that point. This is a T21 model. Most of you in the room were born after spectral models at this resolution stopped being used, but the point is important. There is a parameter associated with the efficiency with which orography generates gravity waves in this parameterization. The notion of the developers was that it was between 0 and 4 and it had a fixed global value. But we went ahead and estimated this parameter at every grid point in the model, and the results are shown here. The stuff over the ocean is just noise, but the stuff over the northern hemisphere, especially western North America, are actual values suggesting that the model needed more roughness there. But the really interesting part is that by far the biggest and most significant values are over the maritime continent in Brazil. What the heck? Okay, so we need a lot rougher land there to do whatever. Now it turns out that this is telling you that our cumulus parameterizations for drag weren't in existence at that point. And so this estimation was trying to find, say, well, we should make the surface really rough to fix this. The key point here is, first of all, this revealed a model deficiency and suggested a solution. The second key point is it didn't answer the question that the developers expected us to answer. What it told you is, here are the values for this parameter that give the best fit to observations. Maybe those are not the values that are consistent with how you're thinking about it. And again, this is extremely important when you're designing these things to realize that these issues can come on. I have to tell this one, even though I'm going to run out of time. I also ran, I could not find the slide for this, I ran an estimation at this same time for little g, okay, meters squared per second, the acceleration in CAM. It gave a value of about 8.6. Again, you need to think very deeply about what this means. This is not an artifact in some sense, okay? It's the question that these optimization problems, the sensitivity problems we've been talking about and these other things will give you. What does it mean if it tells you that little g is 8.6 when you start applying that to parameterizations where you don't have any idea what the real values are? So it's important to keep these challenges, but also the capability in mind. Quickly, this is what I was originally going to talk about until I saw the other talks in this session. We have recently developed in DART extremely powerful new methods to take into account boundedness and nonlinear relations in ensemble data assimilation. On the right of this panel, this is just a particular example with one bounded variable, which could be a parameter in the vertical, and an observation of something else, which could be something like temperature. The dark blues are what happens with traditional data assimilation, and the kind of grayish stuff, which would be a beautiful cyan if the red existed, tell you what happens if you use these new methods. And the gray is the right stuff done by a huge MC. So there's huge advantages on this. As one example, it could get rid of negative values that we showed in that early example. Now I'm going to skip over the next part quickly. This is an idealized example of doing a simulation of a tracer. The tracer field in this idealized model is shown drifting off across space on the right here. I'm constrained by time, but these new methods vastly improve the capabilities of data assimilation. In these plots, the dark blue is the truth for these things. The ensemble mean is what should be red, and the greenish is what should be the ensemble members. If you actually use these new methods, you get rid of this bias, you get rid of negative values, you get a better fit. But if you go ahead and try to estimate sources on this, there's a single source in this idealized example, you are unable to unravel and distinguish entirely where the source comes from. Okay, does it all come from grid point 1? And the answer here, grid point 1's value, which should be 5 on the left there, shown in blue, the estimate says no, it's around 3.5. And you get non-zero, but fortunately non-negative values for the other ones here. This is an example of an observability problem. There simply isn't enough information here to distinguish between these different parameters on what the source is. And again, you have to be aware, even with your Latin hypercubing and other things, about these possibilities. I'll stop for now with conclusions left on the screen. I've hit my 10 minutes, and I'll take my one question if there is one.
Hi, thank you for the excellent talk. As part of a project that I'm currently working on, it adds radial dependence of gravity back into the dynamical core. And my question for you is, we've seen a lot of backing out a estimate from an ensemble, but is there a way to use data assimilation technology to design experiments or to elucidate causality? Or is that beyond the capabilities of what that technology can do?
So I would say any of the methods we're talking about here are basically correlative methods.
Yep.
Right? And so there are people who want to talk about causality, and this, for instance, Peter-Jan van Leeuwen, who is a leader in this field up at CSU, has been thinking about this, but challenges abound. And so I would say I'm pretty conservative about this. Correlation isn't causality, whether that correlation is linear, nonlinear, or whatever else, but it gives you a hint at what causality may be. So I think it's not a panacea for that.
Thank you.
Our last question, well, we still have some time for discussion at the end, so we'll get to you. This brings us to our last presentation of this session by Yang, who's going to speak to some lessons learned from applying these types of method to a different model, the NASA GISS model.
Hello, everyone. Thanks for joining this discussion. My name is Yang. I work as a postdoc for Columbia LEAP. And before I started, I need to make it clear that most of the slides are contributed from the two authors here. So we all know that ESM models are subject to lots of physical processes, and there are lots of parameters that control these processes, and definitely how we determine the values to determine the value of these parameters is critical. And of course, we want to determine these values so that with these values, the output of the ESM could produce relatively more realistic results compared to what we observe about the Earth. Of course, this is important because we have a better constraint of the future climate projection and its associated uncertainty. So a common issue that we run into is the equifinality. So it's like we have lots of parameter combinations and they lead to similar results. There are good and bad reasons to it. Partly it's because there are it's high dimensional problem, so it's natural to have that. It also reveals very complicated processes that the ESM is running. And at the same time, there's uncertainty from the observation and in the emulator. So here is our case. So we run the NASA GISS climate model atmospheric component. I'll skip through these things we've talked about. So supposedly we need to run the MCMC, but we use neural network as a surrogate model to replace the computationally very expensive numerical model. So we draw from the posterior distribution. So that's basically the framework. And an additional component that we kind of want to stress is the observational uncertainty. So to sum it up, in the middle panel, that shows the difference between the difference between two sets of observational data sets. So you can see the ratio varies a lot, especially for the first one, from 40 to -40. So we sort of think that, oh, maybe this sort of uncertainty is critical and we need to consider that. So this small figure is actually kind of important, but it's small. So if we just have one set of observation, the arrow function might look like just the one black dashed line. So we came up with a somewhat arbitrary kind of penalty or arrow function. That is the very slope green dashed line. So you can see, like the edge of these green dashed lines are kind of the observations. So we think, oh, if the prediction of the GCM is within this observation range, we just think they're equally good. It's all good, no difference. And by some manipulating of the function format, we make it very very steep outside of this range. So this will be important, and we'll see its effect later. And this is a very complicated figure. I'll summarize it real quick. So this column is the observation. This one. This one is kind of the bias from the observation with respect to the default. And the third and fourth columns are from like posterior distributions of this workflow. We just draw two samples and substitute it back to the model and compare its difference. What we notice is that for the first three rows, you notice there's not much difference. So it's actually kind of nice because it seemed to suggest we kind of realized this like multiple optimum solutions. So we find the diversity, different regions in the parameter space that gives you similar results. So that's good because we provide alternative configurations with respect to the default. And in the fourth row, we're happy to see that for some variables, it even has some improvement. So for the default bias, you see lots of dark blue there, and it gets brighter, and the arrow is relatively small for here. So that's kind of the two lessons on a broad general level. And diving into the details, there are kind of two results. So the scattered plots here, you can see the X and Y axis are the GCM output, and the black dots are sort of the LHS sampling results used to train the emulator, and the green and blue are different kind of posterior distributions we draw after the training. So for results one, the lesson is that for some variables, for these two variables, our workflow, like the posterior distribution of the variables, really explain what we observe really well. So it's like, they call it crosshair, I guess. So it's right on. We're really happy about that. But for results two, for example, this y-axis variable, it just never match into the range of the observation. And at first we thought, oh, maybe it's because of the emulator. But if you look into the details, the training data, the black points, also there's very few or none black points. So that's the real GCM output from the LHS that kind of concentrated around that area. But also this kind of exposes the problem of emulator, because we don't know if it's because the sampling is too sparse. So that's definitely an issue. So this this posterior distribution here is kind of this highlights the difference between considering, so it's showing the importance of this arrow function design. We just focus on the yellow and blue bars. They are the posterior distribution, considering and not considering the arrows, like the arrows in the observation or the two sets of observations. So the yellow bars assumes, so it's the steep thing, and the blue bars are more conventional. So you can see just by including this arrow differently, the posterior distribution could change drastically. So we think that's maybe pretty important. So I'll skip the first row. It's kind of it's too much details into it because of time. But so for now, what we're working on is we hope to improve the emulator performance. So we kind of have this vision for what a good emulator should be. So of course, it should avoid overfitting. So myself, when I work with neural network, I run into lots of overfitting, and I never, say it out loud. But also also this is related to the sampling density problem, because we should be able to estimate the uncertainty, and the uncertainty also should vary by within the parameter space, because some regions maybe it's never affecting the output, and then it should have a lower, it should have a greater uncertainty, but maybe it just doesn't matter. So this is a visualize. So yeah, so we're doing some data exploratory. So figure on the pane on the left is just a correlation heat map. On the right is just kind of a measuring if the variance changes with just one variables, and we highlight a few examples. You can see some of them increase linearly and with a change in the variance, some are not, and different kinds. And we definitely cherry pick a little bit. So these are like just to show you what we've been working on. And so we're trying to came out with a good emulator. We need to know what the data structures are. So we sort of kind of identify three. So first we notice that, of course, there is some structures that's kind of linear. If you plot it on a biplot, everybody could recognize it. So that's the lower left one. And the second point is that for these important linear variables, they also have their interaction. So that's the 3D plot and the arrow that it points to. So you can see definitely these two variables are not independent. But we also notice the local variabilities. It's very strange that sometimes, so in this case, the surfaces I'm showing has some arrows. We're just feeding it to a Gaussian process to show it to you. So it's like so the variables, the x and y, are DCS and VF multi. But strangely, when we subset the data based on other variables for subset A, scale CN, and then we fit it again to the emulator, you can see the subset A and subset B shows not a greatly different, but slightly different surfaces. So for now, I examined myself, and I think it's probably something interesting that worth exploring a bit more. But I also need to stress that it's very likely to be the result of overfitting. Because when you take the subset, there is fewer and fewer data, and the credibility of your fitting just becomes less reliable. So I'm just listing everything in here, and the most important point is we hope that these lessons could be informative to all, and we, of course, as a community, encourage and look forward to collaborations. Thanks.
Discussion, so you can feel free to ask questions to any of our speakers if you didn't get a chance to, or we can open it up to broader discussions as a community about some of the themes we heard throughout the session.
I had a question for Jeff. Actually, I remember Jeff's plot from 20 years ago. I really do. So what is the message from that if you're trying to estimate a few parameters, but not all the parameters, the few parameters will try to compensate for the ones you're not estimating? And does it have implications for things like emergent constraints, that they're compensating errors there as well?
Because there will be many other issues. I think it is more one of decidability in many cases, is that within the parameter sets that we have developed in many of these models, and this is related to the last talk in many ways too, it is unclear what the optimal set of parameters even means. Do you want the optimal set of parameters to be the ones that best fits the observations? So as a sort of data simulation theoretician, that's what I want. But our collaborators, you remember that slide, and nothing ever got published because our collaborators were so grumpy about the fact that it gave all these values that were outside of the range of 0 to 4 that they just ignored it. I think the one outcome was it did convince people that they needed to put in cumulus momentum drag into CAM 4, I believe is when that was implemented. Yeah, I'm not, can you repeat the part of the question about emergent at the end?
People use emergent constraints to estimate parameters, but they do the scatter plot and say observations is here, so the right value is over there. But there also you get these compensating errors that could be there.
These results here are not related to doing it with ensemble data assimilation itself. It's a fact of the statistical problem you're trying to decide, and it's simply, there's no deterministic answer to these things. The other thing to keep in mind is uncertainty quantification was part of the topic of this too. As soon as these things are compensating, you cannot put uncertainty bounds on the estimates of these parameters anymore when it starts doing that. It's not even meaningful to think about putting uncertainty bound on these things when you could say, well, I could fix it with this, or I could fix it with this.
We have another question for Jeff in the chat. Is this on? Can you hear me? Okay, yes. Really cool talk. I am just curious what the nonlinear DA method is that you're using. I think a fair number of our parameter estimation problems aren't too nasty based on staring at our parameter posterior PDFs. Could be really nice targets for DA, and that's from Marcus Van Leer-Walke. Great.
So these nonlinear methods, I don't have time to talk about them today. They are documented off of our webpage, and you can also contact us, our webpage, which was dart@ucar.edu. These methods basically make use of transforms involving estimates of the distributions of the distributions that are associated with the ensembles and ensemble data assimilation. There are some limitations on these things. They do not uniformly solve stuff, so the whole particle filter cursive dimensionality is still hanging out there. But for bijective nonlinear relationships, they are extremely powerful, and they are by definition, they will respect bounds that you put on distribution. So that one I showed at the end very, very quickly for a tracer transport, that bound of 0 below there, you could say, I know tracer's concentration doesn't go 0. You can tell the assimilation method that quite transparently, and it will do a statistically consistent solution of that will respect those bounds.
I actually have a question for the first talk from the organizers. These PPEs seem like a really awesome tool for testing the sensitivity. It'd be great if we had this in sea ice, which we don't in the coupled context. I guess I'm wondering, how were these funded in this? Like, is this done under base funding? Is it done under, project funding? Like, how do you actually go about getting the money and personnel time and all that to do this type of sensitivity analysis?
Question. I think it's probably a little bit different for the different projects. I hope this is on. Some of the work that we're doing with the land model is through the LEAP project at Columbia, where they're interested in machine learning, using machine learning to improve CESM. But I think, like what we just saw in the last talk, that this interest spans across different models. And so we don't want to necessarily limit the work just to a particular model or a particular model component. And we've seen that when we are able to sort of cobble together, different people's time to run these large ensembles, they do get a lot of use in the university community. So I don't really have a good answer for you, but I'm encouraged to hear that you're interested in doing this for sea ice. And another thing we're interested in is sharing, tools that we've developed for parameter sampling. It varies a little bit by model component in terms of, idiosyncrasies in the spin up and things like that. But I think it would be great if we could share approaches more broadly. So good question, though.
Can I partly answer that as well? That I think with each project it's different, right? I think with the CAM is Andrew had a project that he got funded. I don't know which organization. And with CLM, it was sort of spearheaded by a little bit of base funds, and then also we had an ASP postdoc who was interested in it. So it's just catch can as we took advantage of opportunities. So yeah, there is no one answer, unfortunately. But we are seeing that the benefit is paying off. I think manyfold. I actually had a question for Yang, if that's okay. When you showed that, when you're showing the parameter estimation, and you have the case where had nice overlap with the observations, and you could find the optimal parameter sets, the green dots that were in the crosshairs, and then you showed the other one that was like way off. I'm curious what happens there in the calibration. I guess it's trying to get as close as possible, but that may actually be a not very realistic parameter set because it's just revealing a major structural problem in the model, in which case you might be pulling it into some weird regime. So I'm curious how you guys address that, if any way, or just let the math try to figure it out.
Thanks for this question. I think, like you said, it's possible that it's just like it could be some structural problem in the model, and I'm just repeating myself, I guess. But also, it's possible the sampling is not dense enough. We're missing realistic area in the parameter space that the model just didn't run. So that's why I think the overfitting and being able to estimate uncertainty is a critical issue, because it's also possible, like when you that's kind of my answer to it. Is that what you're?
So it was so far off that it kind of implied that you could have run more parameter sets and you wouldn't have gotten any closer, would be my guess, right? So there was no parameter set that was going to give you the answer. So I'm just curious, what's the best practice in that situation? Like maybe you should abandon trying to use that diagnostic or something like that, because if you do use it, it's going to try to pull you into some space that's just like unrealistic for the model configuration we have.
Yeah, I think that's absolutely true. Yeah, and that's definitely an issue we need to consider more. And also, it goes to the discussion of the metric, and it's all get connected. Yes, thanks.
Question for you in the chat from Duncan. Really nice talk, thanks. How do you deal with the curse of dimensionality when incorporating multiple observations? Do you have plans to explore, including higher dimensional jobs, for example, maps of satellite retrievals?
I think I'm not an expert in the kind of retrieving the observational data set, but I think the curse of dimensionality is what I've run into is in the end it's because when you take subsets, lots of interesting features start to show, but you cannot take subsets infinitely because of the curse of dimensionality. So the answer is we don't have an answer now. Yeah, thanks.
I kind of would like to add to that a little bit. We've been experiencing the same type of challenge in the land model calibration, and we're thinking about using an ensemble of emulators where we train to an individual cost function or output metric at a time, and then use all of this ensemble of emulators to construct a error at the end, right? Rather than trying to just train one emulator to a compound cost function. If that makes sense.
Yeah, I have a question about probably something hope the PPE group or Yang and other people can discuss. So the emulator has been used by many studies for the PPE parameter estimation or uncertainty analysis. So I noticed that most studies try to build or improve the emulator performance in one region, or most studies use a few or probably single emulator. I'm interested in large sample modeling. For example, I want to build emulators for many regions or many watersheds, and that will be related to the universality of the emulator. So for example, Yang tries to improve the emulator performance, but when we want to build the emulators for many regions, is there a way we can improve the applicability of the emulator in a smarter way? Because for large sample studies, we cannot manually to adjust the emulator structure or like input-output relationship. So just want to hear if there are any comments or opinions on this problem or challenge.
Have some thoughts about it, but it's not very successful. But in the end, it's kind of the metadata of the model that you train. That's the universal part. It's, for example, I work with, like, I realize, like, sometimes the different dimensions, like dimensions 1 and 2, they just like conjugate so much that I cannot separate them, but at the same time, that's a useful information for the future emulator development. So somehow I think it's on another level. Yeah.
I think there are meta-learning methods that may be able to bring together some of these different, bring together a more universal approach like you're inferring. And we can talk about this later, but it is 6 o'clock, and so we're going to wrap up the session. Thank you all for bearing with us through many technical challenges. We appreciate it, and we do hope to keep this discussion going and keep this community talking and communicating across working groups. So yeah, please reach out if you're working on related projects or if you just want to get involved, and we can start bringing these groups together more regularly, I hope. So thanks again to all of our speakers.